will go into data mining. Some of the data mining tasks, I just wanted to give a introduction into what kind of data mining tasks are there. You might have heard this, as I said, you have all been in the FTP for the last few days, and some of you are probably in the domain for quite some time. I'm just trying to give a quick introduction here. So classification is kind of a predictive analytics technique where we try to predict the class of each of the data point. That's I think it doesn't need much definition on its own, but classification is the discrete class labels that we are trying to predict. That's what the classification is. Some of the examples are credit card propensity, which says if we are offering as a bank, let's say if a bank is offering a customer a credit card, we are trying to predict whether the person or the customer is interested or will accept the credit card offer or not. That's a yes/no problem where we try to predict whether the person will take it or not. And then we have a classic example of spam emails. So we are trying to we are trying to categorize or classify all the emails that are coming into an inbox to say whether it is a spam email or not. That's a classification problem as well. So that's the classification type of predictive analytics. And there is regression type of predictive analytics where the target variable is a continuous variable instead of classes, like what we were just discussing. It's not a yes/no problem, or it's not a spam or not spam problem, but it is a continuous numerical variable is what we're trying to predict. Couple of examples are we might actually try to predict how much a person would spend on their credit card in a given month. That could be anything between 0 and the limit of the credit card. So it's a continuous numerical variable that we are trying to predict. So it becomes a regression problem. And another example is that trying to predict the value of a house, the house price that we are trying to predict. Again, that could go anywhere from, let's say, $10,000 to about $1 million. It could be any value. So it's a continuous numeric problem that we are trying to predict. The target variable is continuous, and it becomes a regression problem. Similarly, we have another a technique called clustering, which is most of the times we think it's a predictive model because there is an algorithm that we are running to do the clustering part. But I am classifying it as a descriptive analytics part because the clustering happens on the data that is already known. We don't have to create any future data points, or we don't have to predict anything in the future. We already know all of the data elements. All we have to do is putting them into different clusters, whereas each cluster is tightly related within the cluster, and it is a little farther from the rest of the clusters. Again, as I said, I define it as a descriptive analytic technique rather than a predictive analytic technique. But yes, there are machine learning algorithms that we use to do the clustering. But again, it's with all the data that we already have. One of the examples is customer segmentation. This happens, I think, with all the institutions or companies that have customers. They try to segregate their customer base into different clusters so that they can cater to the needs of these customers individually, so that they can address their needs in a more targeted way. Like, for example, if we take a bank and all of its credit card customers, there might be customers who will be spending out, let's say, up to $100 a month. These people are the low spenders, and they might be interested in some sort of credit card offers, where you say, hey, you get 10% back cash back on the grocery store. That is a policy, or that is an offer they might be interested in. And there might be another set of customers who are very high spenders. They spend let's say thousands of dollars every month, and most of their expenditure goes into, let's say, air travel. if we want to like, so if the bank wants to cater to their needs, they are more likely to accept an offer if the bank says, hey, you get like 10% cash back on the air travel instead of the grocery stores. So they will sign up for that offer for that credit card. So it's important for each company, each institute to segregate their customers into like clusters and um, and cater to their needs independently. And another example could be a document clustering. Let's say you have a list of all the documents that are available in institute. I was about to say in a college, right? You have a college and you have all the documents which are applicable in the college setup, like admission forms or fee forms. All of these documents are instructions, class instructions, and class material and everything. So you have all of these documents, and you want to like cluster them into different sets and say like, hey, these documents are related to administrative building, these documents are related to classroom maintenance, and this some other set is related to something else, right, in a college setup. So that could be addressed as a clustering problem, where we are trying to cluster all of the documents into different clusters based on what they are related to. That's about clustering. I'm taking a small break here to see like if anyone has any questions so far about classification, regression, or clustering.
No, sir, it's fine.
All right. Thank you for the confirmation. And then we're moving on to the next three types of analytics. Visualization is again obviously a descriptive analytics method, because visualization is nothing to do with in the future. It's with we visualize the data that is already present, that happened in the past, and we create all the charts. Like again, as I was saying, we create pie charts, we create bar plots, we create vertical bar plots, box plots, and anything that goes into a visualization technique, and these are descriptive analytics. And similarly, there is a technique called associate rule mining, or associative rule mining. And again, this is also a descriptive method, though a lot of times, just like clustering, this one also falls into kind of machine learning algorithms, but it's not exactly very predictive or futuristic prediction, because the associate rule mining is trying to create groups of items that generally go together. So, the one of the most famous examples for that is a market basket. So if we take a supermarket, right, and all of the customers who come into a supermarket, they have hundreds and hundreds of varieties of items they could buy. And many a times, if we observe that, most of the people who buy, let's say, this is a very interesting example. Most of the people, there is a study that was done in US, and they found out that most of the people who come to buy a beer in the supermarket also buy milk for babies or something. And I think that is just association of the items. That's what the association rule mining does, right? I'm like, all you know is that each bill has like so and so items, and if you say, hey, 10 out of 12 bills, 12 receipts have both beer and milk in their receipts, we say that, hey, beer and milk are associated with each other, because most of the people who buy one also buy the other, right? So that's more like correlation between the items, but it might not have a causation. And if you think outside the machine learning models, we might actually think most of these people who are coming to buy beers like once in a while, they might be fathers, like who are coming to store to buy milk for their babies or even for the families, right? So that is more likely that is the causation behind it. So that's associate rule mining. Again, I was saying I categorize this as descriptive because it doesn't say anything about the future, but once you know the rules, like, from the past data, again, as I was saying, we know that 10 people out of 12 people who are buying beer will also buy milk. We can apply that rule for the future. Like if someone's getting a beer in the future, we could assume, hey, these people might be interested in a beer as well, and we could, like, the supermarket could put them next to each other. Like, there is a fridge with the beers, and there's a fridge next to it with the milk products. So that's how we could use it for future as well. But the data and the inferences are coming only from the past data. So that's why I call it a descriptive analytic method. And then another descriptive analytic method I am most interested in is graph mining and network analytics. We saw an example yesterday, and we could actually kind of say the same for social network analytics. That's a very good example. And yesterday I was describing this example. Like Facebook, LinkedIn, Twitter, all of these companies, they have a recommendation engine that does all the graph mining or network analytics behind the scenes so that they can refer or they can recommend new friends, followers for you with more efficiency. And that's one of the descriptive analytics technique to identify who you would be more interested in connecting with. That's different kinds of data mining tasks. Some are predictive, some are descriptive. Any questions so far? All right, I take it as no questions. In the next slide, we will see what happens in a data mining task. Like, let's say if we receive a problem, what are the steps that are involved from the beginning to the end of the project, right? So we start with understanding the business need or the project goal. Like in terms of a corporate setup, the business need is the goal of the project. We start by saying, hey, what is the requirement? What is the need that you are trying to address? That's the business need. And there is like if in case of academia, it could be a project that you are interested in working on, and you come up with the project goal, and you start searching, for the data for that particular project. And one thing to remember here is the business need many a times might not need a data science solution or a machine learning solution. Many a times it could be simple descriptive analytics as well, what all the business unit needs or what all it takes for a project. So just because we have a hammer, we don't have to hit everything as a nail. So we'll have to think what is the easiest way of solving this particular problem before we jumping into saying, hey, I know machine learning and I know data science. Let's solve this problem using data science and artificial intelligence, right? We don't have to do that. All we have to do is understand that business need. What is the need of the business, and see what is the right analytics technique to address that business need. That's the first step in a data mining task. And the second step is to obtain the data that is needed for analysis. So you know the problem now, and now what you have to do is you'll have to start searching for the data that can answer this question for you. Like, for example, in today's hands-on session, right, what we will do is we are going to try to predict whether a patient who is discharged will get readmitted to the hospital or not. That is the goal of the project. And what do we have to do is we'll have to find the data that will help us answer this question, right? So what we'll have to do is we'll have to know some demographics about the patient. Hey, how old is the patient and where is he from? And sometimes the race of the patient might also help in predicting whether the patient will be readmitted or not. And what was the medication he has taken or he or she has taken in the first visit, so that we know, that might help us to understand whether the patient will get readmitted or not. Like, some of the medications are associated with, let's say, long-term diseases, and they might indicate that if it's a long-term disease, they might indicate that the patient might get readmitted sooner or later. So these are like these. So what we need is a data set that gives us all of this information. That's what we do. So we searched for a data set like that, and I found a sample data set on Kaggle.com, as I said. So we download that data and we use that data trying to predict whether the patient gets readmitted or not. And then the next step is, once you collect the data, actually, before I move on to the next step, on the data collection side, many a times we might actually start our project thinking that, hey, this data set is useful for us to predict something or to do the analysis that we need to do. And we get started with it. And after a while, you might realize that probably having a little more information or a little more features is what you need to solve this problem. So that task of like obtaining the data needed for analysis, though I have written it in one step here, many a times in reality, that will extend to like further steps in the list here, because once I do like some exploration, some cleaning, and then do all the exploratory data analysis, I might realize that, hey, I think this, after cleaning of all of this data, we realized, hey, this data is not enough to do the prediction that we wanted to do. So that's an iterative process. And then once we, let's say we have our initial list of data sets that we think like, we can use for predicting something, we start with exploring the data. In the exploration stage, what we do is like, hey, what are the data elements that are in the database, and how are they populated, and do we need to clean this data? Like, do they have any null values or missing values in the data set? Or if there are any outliers in the data, we'll try to identify all of these before we start any of our analysis. And we do some graphs like visualizations to see this number of missing values or outliers using some visual inspection rather than doing all code or tabular data. That's one of the initial steps in the data mining task. And we will see in the next step, how do we actually go about cleaning the data based on different conditions or based on different states of data that we collected. That's coming up in the next slide. And then we reduce the data if needed. If there are like any unnecessary variables in the data, we'll get rid of it. And then many a times, I don't know if you have heard of this term, there is a term called curse of dimensionality, which means that many of the machine learning algorithms might get affected negatively if the number of features or like number of attributes that we are using for prediction is way more than what the machine learning algorithm needs. So sometimes we do the dimensionality reduction to reduce the number of features. And sometimes we do feature engineering and we create more variables from the existing features or columns. And then we determine like what type of data mining task is it, like what are we trying to predict, whether it is a classification problem or a regression problem or a clustering problem, as we were just talking about in the previous slide. So we make our decision based on, most of the time, these decisions are based on what is the target variable, right? What is the target that we are trying to predict? If it's a categorical variable, it's a straightforward classification problem. If it's a continuous numeric variable, it's a regression problem. And if there is like no target variable, but we are trying to put all of the data elements into different clusters, that's a clustering problem. So any questions so far? No, sir, it's clear.
Sir, I have a question. Sir, regarding dimensionality reduction, is it reducing the unnecessary constructs in the model?
It is reducing the data. Good question. It is reducing the data that is going into the model. It's not constraints of the model, but it's the data that is going into the model. So let's say I have like, for example, that we are going to see today, let's say I have about 100 variables about all the patients, and where I'm trying to predict like, whether the patient will get readmitted or not. And some of the variables are, I'm just taking an example, some of the variables are whether they had breakfast today or not. That's a variable. I have a yes, no column on it. And that might be a column that is not very useful. And just like that, I have, let's say, 1,000 variables in the data set. When it comes to machine learning model, as I said, like, many a times there might be like a finite set of variables that will really help the machine learning algorithm. And if you go beyond that number of features, generally the performance of the machine learning algorithm will diminish because, we are giving it more noise than signal to predict something. Did I answer your question? So it's the size of the data in terms of number of columns or number of features.
So if we have in our model all the variables, then the model won't perform in an optimal way.
It depends. I'll actually show you a way of checking it in the code as well, like in the Python program as well. So there is a way that you can check, hey, what happens if I use like more variables?
Thank you, sir.
For a model. Yeah, we'll see it in our code today. All right, any other questions? I'm just giving you 5 more seconds. If not, we'll move on. All right, let's move on. And then within the data mining tasks that we decide to use, right, like let's say classification or regression or clustering, there are like n number of machine learning algorithms available today. So you could pick any kind of machine learning algorithm to go with it. I just listed some of them, like either decision trees or random forest RSVMs, RSYNs. There are like even regressors that came out of classification algorithms, like now there is a random forest regressor as well. So you use the same principles of random forest classification, but you use it as a regressor model. So there are like a variety of algorithms that we could use. So we will choose one of the models to get started with. And one thing to remember or to note about these choosing the data mining technique, right? You will get started with something, but that might not be the final model that you are ending up with, because many a times you learn one of these models is doing very good for the given data set compared to the other models. It's not universal that a particular model will do best with all of the data sets in the world. So sometimes a linear regression model or a logistic regression model that you are working might be as good as or probably better than a random forest model or a SVM classification model. So this is not like a finite step. You choose the data mining technique and you'll go with it and you'll get the best results. You'll have to like do the iterations of it and see what model is working best for the given data set. So that's the next step, and in the process, we iteratively develop that algorithm. I think I already jumped into the topic without knowing. So you actually iteratively develop this algorithm. Sometimes you actually do the parameter optimization. You go with a grid search and search for like all the combinations of input parameters for this algorithm, and you will come up with what is the optimum numbers that you want to use for this algorithm, and that's one step. And then the other step is, as I said, probably one of these models is doing better than the other, so you'll experiment with a variety of algorithms as well. And then we get the results. And I say results interpretation. The reason for that is seeing the results itself is good enough, but there are different metrics that we can calculate from the results. Like, you could calculate accuracy, you could calculate precision, you could calculate recall, you could calculate F1 score, and you could calculate for a regression problem, you could calculate MSE and RMSE or an R-square value. So there are like different ways of measuring the performance of a machine learning algorithm. And we look at that results and see, hey, which metric do we want to consider based on the business need or based on the problem definition, and then we interpret the results using that particular metric, and then we go with, hey, this is what is looking best for this particular problem, and then we do that. And the final step would be, after discussing your results with the client, who could be internal, external. After discussing the results with your client, you'll deploy that model in production. Sometimes you have to scale it up, because when you're developing the algorithm, you don't have to use the entire data that is available. Like, for some problem like Facebook, if I take Facebook's data, I'm trying to recommend friends for someone. There are like about 1 billion people on Facebook, and I don't have to analyze everything in that data to see, who should I suggest as a friend for a particular person, right? Sometimes you start with a sample, you do the algorithm, and you optimize the algorithm as much as you can, and then you deploy that model in production by scaling it up for the entire population. Any questions? I'm asking again on the slide because this is one of the bigger slides, and this one has like all the steps that goes into our model development.
The data pre-processing is considered the maximum, it takes the maximum part of the data mining process.
That's a good statement. I don't think it's a question, but that's a good statement, and I agree with that. Up to 70% of data scientist time will go into the data, identifying the data and pre-processing the data. And you can see it today. Once it comes with the model building, all you have to do is that there is a function for building a model, and you write like a couple of lines of code, 2 lines of code, and it gives you the prediction already. But what happens before that step is the major time-taking process, and that is the data pre-processing step. That's right. Any other questions so far? All right, I take it as no more questions, and let's move on. And it's again about the same topic we have been talking about, the data pre-processing. And what do we do in the data pre-processing step, right? It depends on what kind of problems do we have in the data. And one of the major problems in any real world data set is missing data. Like, you'll have null values or missing values in majority of the columns or most of the columns. And what do we do about it? I just provided a couple of examples here that what you can do with missing data. So what you could do is you could eliminate the entire rows. Like, you say, hey, I have 100,000 rows, and out of those, 10,000 rows have null values in more than 10 columns. And you could decide to ignore those rows, 10,000 rows, and start working with the rest of the 90,000 rows. When the data is like abundantly available, where you have like enough number of rows, this is an option. You could ignore that row. However, in a real world scenario, most of the time what we do is the data imputation. So based on the null value that is present, like based on the type of the column that we are looking at, we have different data imputation techniques. For example, if the column is numerical column, like someone's age, if we are missing that one, let's say there are like 100,000 rows and the data is present for 90,000 rows, but 10,000 rows have like null values in the age column. One of the ways you could fill those 10,000 rows is calculating the mean of all the mean or average of all of the other ages that are present, and you populate that value for the missing 10,000 rows. That's one of the techniques. And if we talk about categorical variables, like let's say in the example that we're going to see today, there is a column called race or ethnicity, and we see the data has about 2,000 missing values. And what we could do is, right, you could use the most popular race to fill this missing values, or you could also create a new category saying, hey, this category is unknown. So you can make it just unknown and treat it as a separate category. And that's what I have done in the process today. We'll see it in a bit. So that's another way of like imputing values for categorical variables. And numerical variables, we use mean, median, whatever, based on the column, based on the type of the column. Or sometimes we actually make it 0 as well. Many a times, some people do that. If it's a column that can take 0, we can impute zeros into that column. That's the data imputation technique. And then you could probably ignore the missing values in your entire analysis, right? I'm like, you take it out from the exploratory data analysis, take it out from the predictive analytics, don't even worry about it. Now, that's not a great option, but that's something you can do, absolutely. And then there could be duplicate data as well. So duplicate data is when we say, hey, like in the example today, we'll see some duplicate data as well. So the duplicate data is where you have more than one observation for a given ID. In case of patient readmission prediction, given ID is patient number. And if there are like more than one row for a given patient, we don't have to use the duplicate data, right? We'll only use one of the rows. And I kept the first one and I deleted the rest of the occurrences of that particular patient. So that's deduplication technique you could use. We'll remove the duplicate data. Either you keep the first, or you keep the last, or you keep one random and remove everything. It's up to us to decide. And sometimes you can actually think of like chronologically and say, hey, keep the latest data and remove all the historical and previous data. That's a valid way of deduplicating the data, the data. And then there are outliers in the data as well. So outliers is where, generally speaking, outliers is the top 5th percentile and bottom 5th percentile in terms of machine learning. When we do that, we consider like the top 5 percentile and bottom 5 percentile as outliers. And when we have outliers, there are 2 ways that you could, again, handle outliers in the data. You could remove the entire data elements. Like, as I said, if there are like 3% of the rows which have, top 5% of the values, you could remove those rows from the model data itself. Or you could do is you take what is the 95th percentile value for that particular column, and then cap everything at that level. Like, for example, I'm just picking some random example. Let's say we are talking about age, and there is like in your model, model data, you have like 95% of the data or 97% of the data which is under 100 years, and there are like 1% or 2% which is above 100 years. The age of the people is above 100 years. You could keep it as is, as long as like you think it is valid. But if you think it's an outlier, because let's say you have 100,000 rows or like 200,000 rows, and then there is only like a couple of rows where the age is more than 100. It's possible that it could be a data entry error, that the person's age is more than 100, or it could be legit as well, but you can decide whether to cap the age at 100 years, or you can remove those 2 rows thinking, hey, this could be a data error. We don't have any population which is more than 100 years of age in our data sample. You could remove those rows as well. That's another technique for capping the outliers at the 95th percentile, or whatever you think is the maximum value that can be for a particular column. And then we have a sampling step that we do. As I was saying, right, if there are hundreds and hundreds of millions of data available, we cannot develop the machine learning algorithms using all of the data. So we'll have to, majority of the time, we'll have to use sampling to use a portion of the data to develop our model. And then once the model is developed, we scale it up for the rest of the data when we deploy the model in production. And there are like different ways of sampling. One is random sample. In statistics, that is the easiest of the sampling techniques. You just take randomly about, like, let's say I only need 10,000 rows out of 100,000 sample, or a million sample. I'll just randomly pick 10,000 rows. And there is a technique like with and without replacement. So with replacement is that you have like 1 to million record IDs. You pick a record ID, and if you're using with replacement, there is a chance that you can pick that row again, because you keep that row in the sample pool again. And then when you randomly pick another row, you might actually end up picking the same row again. That's with replacement. And without replacement, once you pick a particular row, you remove it from the sample pool so that you don't pick that row again as a duplicate row. So that's without replacement. You could use either technique depending on the business problem. You could use either technique. And there is stratified sample, where you give a target variable or a particular feature to stratify the sample. Most of the time we use the target variable as the stratification variable. The reason for that is, right, let's say I have this patient readmission data, right? I have in my 100,000 data, I have 10,000 people who are readmitted and 90,000 people who are not readmitted. And I only want to use like, let's say 10,000 sample out of this entire thing, out of this 100,000 sample. I don't have to take random sample of 10,000, because if I take random sample of 10,000, I might actually get only 10,000 samples from the not readmitted 90,000 population, right? So I don't want to have only one class variable or one class data when I'm trying to model the model the algorithm. So what we do is, right, out of this 100,000, I say, hey, I need 10,000 sample, but I want it in the same ratio as how the real data is, right? The real data is in 1:9 ratio. So I want my sampling also to be the 10,000 rows also to have 1,000 readmitted patients and 9,000 not readmitted patients. So we'll keep the same ratio as of the real data in the sample. That's what a stratified sample is. And then there are some feature transformations that we could do when it comes to like numerical variables. We could standardize it, we could normalize it, and some continuous variables. If you have a continuous variable, like again, I'll take example of the age. If you have all numbers between 0 to 100, and you could use it as is, I'm not saying we cannot. And sometimes you might actually want to discretize and create bins, saying, hey, 0 to 10 is a bin, 10 to 20 is a bin, 20 to 30 is a bin. So you could do that as well. That is a transformation. That is the discretization technique. Any questions on the data pre-processing steps? As someone reiterated just a few minutes ago, data pre-processing is the major task in a machine learning algorithm, like, in a project that includes machine learning algorithms.
Sir, as we have large number of data, so finding duplicate values is difficult, right?
Yes, that is possible.
Then how can we identify them, sir?
Right. So we generally, what we do is, right, we deduplicate the data only on the sample that we develop for model development. As I said, like, let's say there is hundreds of millions of population that we are working on. We don't have to work on it. We'll only take a sample of, like, let's say, 100,000, which is 1 lakh samples, and then identifying duplicates within that 1 lakh generally becomes easier than identifying it in a millions of data. And most of the time, that's what happens in at least in real life scenarios. Here, we take a sample and we duplicate the data in the sample.
Yeah. Okay, sir. Thank you.
Yeah, and if you wanted to use the entire data set for a model building, that becomes a very tough problem. Like, dealing with the entire data itself is a big problem in itself, and identifying these duplicates is one of those. And what you'll have to do is you'll have to come up with an algorithm that will take less time to deduplicate. And if you are familiar with like any kinds of data structure algorithms, you'll have to identify a process that uses like big O of n processing time and big O of n processing space, and that depends on the kind of algorithm, right? The deduplicate data, as I said, the deduplication is something that, or even the duplicate data is something that you define based on one particular column or a set of columns, right? And all you need to dedupe the data is not the entire data itself. It could be millions of data, but once you only look at a particular column, you could create vectors with it, you could create arrays with it. And generally, when it comes to Python programming, if you vectorize a function, instead of writing a pure Python program, if you could vectorize that function, the processing power is generally tens and tens of hundreds times of faster than the pure Python method.
Okay, so thank you.
Sure, good question. Any other questions on data preprocessing?
So the last part, vectorization of variables, what is that, sir? Forming clusters or matrix?
So yes, forming matrices basically. That's a good question again. So vectorization is a process of converting your data elements into matrices and vectors. The reason for that is, all of the computers are equipped to process arithmetic or mathematical equations way faster than they can process textual data or image data or any of these, right? So when I say vectorization is that if you have a data set, what you want to do is you want to convert your data set into numerical vectors so that you can process it way faster. As I said, it depends on your processor size for sure, but generally it will be like 60 to 100 times faster than your pure Python implementation. So by vectorization, what I'm saying is you convert your data into numerical NumPy arrays or vectors so that you can execute mathematical equations on it instead of doing a Python function on it.
Thank you, sir.
So one doubt regarding the data. In medical data where the data is really scarce, if I have too much data, I can pick the samples. But in medical data, what happens is there are missing values as well. In that case, we don't really get a large data set for training. How to deal with this, sir? Of course, there are class balancing methods, but when I do class balancing, it goes for oversampling. But is that right, actually?
That's a good question. Well, I did use oversampling, or I did use techniques to balance the classes. That's a good point. But your question is more about how do we actually identify data for medical problems or healthcare problems, right? There is a service called Cynthia, Synthea. Cynthia. So what it does is actually you can download that. It's a Java package. You can download that program itself and run that package. They have instructions to run it, and you can create the medical data as much as you want. You can create a sample of 10,000 patients. You can create a sample of 100,000 patients. You can create a sample of 1,000,000 patients. All it takes is time to generate this medical data, if that is your question. But again, if you're talking about class imbalance, as you said, I generally try to, if the data set is large enough, I try to undersample. I take, let's say I have a true class, which is 20% of the entire data set. I take 20% of the true class, and I'll only take the 20% of false class as well. I'll not take the 80% of that data. I'll only take 20% and 20% each, so that I have a balanced class prediction for my data. And if I don't have the large data set, though it's not the best idea, we do actually repeat the samples. We do replicate the samples of the class that has less number of rows.
Thank you.
Very good question. Yeah, and I'm like, it might be out of context, but Cynthia is a service I really like. I recently started working on a personal project using healthcare data. And again, we came across the same problem. Like, how do we identify the data in a healthcare setup where the data is scarcely available, as you said? So I came across the Cynthia, and then I generated only 10,000 samples for now, 10,000 patients, but the data is big enough already.
So this is from the state of Massachusetts. It stimulates, so only related to health data?
Cynthia, yes, it only simulates healthcare data, and it's mostly applicable in the US. You could leverage the data even in India, but some of the tables like insurance payers and stuff might not be very accurate if you use that data in India. But if you're talking about patients' information, and then if you're talking about healthcare conditions like the disease codes and stuff, it has the international standards for coding all the diseases.
Very useful resource. It's a repository in GitHub.
It is a repository in GitHub. You download that repository and then you execute it based on your requirement. Like, you provide the input parameter with the number of samples you want to generate, and then you can generate all the samples.
Thanks. Thank you.
Sure. All right. Any other questions? We're almost at the end of the boring slides generally. we'll jump into the model building in the next 2 slides. These 2 slides are very helpful, very useful, and it answers a lot of questions. And I would like to mention it explicitly. I did not design these cheat sheets or these graphics. These are designed by scikit-learn, which is a package in Python for all the machine learning algorithms. They actually designed this cheat sheet, what they call is a cheat sheet. And what it does is it tells you like how to pick a good machine learning algorithm based on like different conditions, criteria of the data that is available to you. And we'll start here with the start button here. And if you see if there is like, whether there are more than 50 samples or not, first thing, like, if there is at least 50 rows of data or not. And if there is not like 50 rows of data, they say get more data. I would say actually, if you have 1,000 rows, yeah, go with modeling. But if you have like less than 1,000, get more data. But yeah, they recommend, I think with 50, you could probably start building your model. And then what you look at is what are you trying to predict, right? Are you trying to predict a category or not? If you're trying to predict a category, you will go to the S side of it here, the label data, because you're trying to predict a category. You will see whether there are categories that are already labeled or not. If it's already labeled, it's a supervised machine learning algorithm. You go into this section, that's classification. And if there is label, like we do have, like we don't have label data, but it's a classification, like a categorical prediction, you go into clustering and you use these kind of algorithms there. And if it's not a category, you go into whether it is a quantity or not. And generally, if it's not a category, it should be a quantity, most likely. If not, you're just looking at it. If yes, you will go into the regression types of models if you're trying to predict a quantity. I think as one of the examples we discussed, like predicting the house price or like predicting the spend of a credit card customer, like how much he would spend in a month on the credit card. That's a quantity that we are trying to predict. So we go there, and then in each of these clusters, like this is to create, what are you trying to do? Like, the classification, clustering, or regression. And if you're not predicting either, right? If you're not predicting a category, you're not predicting quantity, you might just be looking at it. If you're just looking at it, you just do whatever you want to do. And then if you are not just looking at it, oops, sorry. If you are not just looking at it, or if you are looking to reduce the number of samples that you are working with, you go into dimensionality reduction, and there are like different types of algorithms that you could use to do the dimensionality reduction. That's a very good path to determine like what to use. And there are like a lot of these algorithms they say, and if I have to admit, yeah, I'm not a master of all of these algorithms. I might know like some of these algorithms most likely, and there is always room to learn in data science. We keep learning almost every day. So yeah, if anyone is interested in finding this one, you could simply do the same thing. You search for scikit-learn algorithm cheat sheet on Google, and you can find this algorithm, the graph, and you can go from there. Any questions on this? I'll only go into the details if there are any questions in this chat. Otherwise, we'll move on.
Yes, the green arrow is yes, and the red arrow is no.
No.
What's the
yes.
yellow arrow indicates?
So many times if it's not working, basically, so I don't know if you can see this, it is written as not working. Let's say you have like less than, probably more than 100K samples, and you go into the SGD classifier. SGD stands for stochastic gradient descent classifier. So you start building your stochastic gradient descent classifier. And if that model, if it's performing, you can stop there. If it's performing well, you can stop there. If it's not working, you want to do kernel approximation. So there are like different kinds of kernel processes that you could use within the SGD classifier, but you could use different kinds of approximations which might improve the performance a little bit. Similarly, like, you try the k nearest neighbors classifier, and if it's not performing up to the standards, you go into SVC or you go into ensemble classifiers. Ensemble classifiers are a quick definition of ensemble classifiers is that you stack up more than one machine learning algorithm into one problem, basically. So you build, let's say, I use one linear SVC classifier, and then I get the result of it. I use that result as features for my next machine learning algorithm, and then I run a random forest on top of it, and then I get more results. And people generally do use this in the experimentation stages. In real life scenarios, we will not do that, because when you are working with a client, you cannot explain an ensemble classifier to a client, because it's not easily explainable, because some of the features you're using are the outputs from a different machine learning algorithm, and you can't say like what is the meaning of it. So yeah, people who are competing on Kaggle to win competitions, they do use ensemble classifiers to improve the accuracy. It does definitely improve the accuracy for sure, but can it be explained? Can it be explained? Generally hard. Any other questions on this slide? All right, I take it as no more questions on the slide. This is the last slide before we go into the coding part. And what I've listed down is some popular models and their pros and cons. Generally, to be a data scientist, all you need to know is the algorithms and how to use them. To be a very good data scientist is when you need to identify or understand what are the advantages of a model and what are the disadvantages of it. That's when you can make informed decisions or knowledge decisions, saying like, hey, for this particular problem, these are the advantages. Like, if I go with this model, these are the advantages and these are the disadvantages, and I want to go with this particular, machine learning algorithm. So I only listed down some of them because these are the only ones, where there is a graphic available for me to download from internet. So starting from the linear regression, right? Generally, the description of a linear regression model is, it is the best fit line through all of the data points. That's similarly, it's the easiest of it. It's y equals to mx plus c, or kind of equation that we are trying to fit with all of the data points. And the advantages of it is it's very easy to understand, because you have an x, all you have to do is try to predict the y. You put it into the mx plus c formula. M is the slope, or the angle, and c is the intercept. And once you have those values, it's very easy to predict using that model, and it's very easy to explain. Like, let's say if I'm using one variable, like the age of the patient, to guess the readmission, I'll say like, hey, if you multiply your age with 0.2, and then you add like 0.001, you get your y. And if your y is more than 0.5, it's a readmission. And if your y is less than 0.5, it's not a readmission. So that's the easiest to understand. And the disadvantages of it is it's very too simple to capture the complex relationships in the data. Generally, one of the examples is, right, you have, let's say, tens of variables, and then all of those will go into different dimensions, and one straight line will never be good enough to address or to reduce the error of the prediction. So that's the disadvantage of a linear regression model. So that's when we came up with like all the polynomial regressions, where you, instead of using a straight line fit, you fit a polynomial line, so that like you go to each of the data points as close as you can to reduce the error. That's for the linear regression. And then, oh yeah, it has an assumption, the linear regression, that the elements or the features in the data set should not be correlated. And if there are like variables which are correlated, it's generally recommended that you get rid of one of the features and keep only one, if like there are two variables which are correlated. And then similarly for logistic regression, it's an adaptation of the linear regression problem, but mostly for, not mostly actually, it's for classification. with yes no types of questions. Again, it's also easy to understand. It's a formula, it's a mathematical formula. You can explain to anybody with the formula, about the logistic regression. It has the same problems as the linear regression, whereas the regression, as it says, it's the linear regression. Logistic regression is the only one which says regression, but it's a classification algorithm. Again, and then moving on to decision trees, you might have, many of you might have already seen this. Generally, we create rules based on the features, like, hey, if this feature is less than this or greater than this, go into this prediction or go into that prediction. It's generally easy to understand because it's a tree structure. You will look at each of the variables and make the decision. It's very similar to linear regression in a way that it can be formulated into a mathematical equation, so that it's easy to explain and easy to understand as well. And the disadvantage of it is that it's generally not powerful enough to work on complex data, because the rules are something that that you'll have to make, and you can't make like very complex rules like hey, split this data into like, in case of age example, you can't make tens of branches saying, hey, if the age is between 0 and 5, do this. If the age is between 5 and 7, do this. And then if the age is between 7 and 10, do this. And you can't create all of those branches like that. Generally, you'll have to make branches like, hey, if the age is greater than 30, do this. If the age is less than 30, do this. Something like that. So it becomes too simple when the rules that you have to build or we have to build is more complex for the data, for the given data. So generally it's not like used on its own. And then we to address that problem, actually we use random forest, where you use the decision trees, but you use a bunch of them instead of just using one decision tree. Use a bunch of them so that you will address, like, instead of creating 10 branches in the same tree, you create like 10 branches in 10 different trees, but you combine the end result into one using the random forest technique. So that's to overcome the shortcomings of decision trees. And generally, it's very hard to explain. It's kind of black box model. We call it a black box model, where we do not have a clear equation of like, hey, how is this prediction being made? It's an algorithm, it has all of it, but once it comes out of the algorithm, it's really hard to map it back to the input source and say, hey, because this variable was this, and then it went into so and so tree, and then it came out of the forest as this particular output. We cannot explain it. So it's a black box model in that way. It's not very easy to understand. And then this model can get very large. This model can actually take a lot of time to train based on the number of trees that it is building and the number of features it uses in each tree. It can become very robust, and it can become a very time-consuming process. And then gradient boosting, it's again another technique that also uses kind of decision trees, but instead of unlike random forest, this one uses a boosting technique where you use, let's say, different versions of samples in different trees, and then you combine that data in the output. Basically, it makes use of, like, I think as the definition says here, it uses the weaker decision trees. Like, it makes decision trees for all the samples. And there could be like weaker decision trees which are giving less accuracy. In case of a decision tree, if it's not performing as well, we just ignore it, right? But what gradient boosting does is it actually uses that information, and it says, hey, this particular decision tree is getting this particular variable wrong, and what can we do about it? And then it starts using that information, and it trains the model in a way that it uses that error, and it says, hey, if another tree is trying to predict this one in the same manner, tell that tree it is wrong, and you'll have to like negate that prediction. That's how the gradient boosting performs, and it's again a high performing model. And a small change in the feature set can create radical changes in the model, and it's very hard to explain. Again, unlike decision trees, it's more like random forest. It's very hard to explain what how each feature turned out to be the output variable. Again, it's a very very black box kind of model. And then when it comes to neural networks, again, you might have heard this in the recent times, like pretty much in deep learning and all the image analytics processes. We use this neural networks, different variations of different neural networks like CNNs, convolutional neural networks and recurrent neural networks. There are like a variety of those. Those are in usage today. And the simplest explanation of neural networks, as people would say, it mimics a human brain. So you have all of the neurons in the internals of the neural network. You send some input variables and it multiplies it with the weight of each of the neuron and then adds whatever needs to be added. That is the bias that we need to add. And it comes out at the other end with an output variable. So what happens in the inside, like from between the input layer and the output layer, is called the hidden layers. And the hidden layers, we don't know what they are doing, right? Because it learns during the training stage, it tries to optimize the weights on each of the neurons based on the data. And then in the prediction stage, it uses that weights to predict what is the output variable. It can handle extremely complex tasks. Like, as I said, it could do image analytics. It could do, in our team, actually, we also do voice analytics. One of the examples is like, we could use a person's cough to predict whether the person is infected with COVID or not. So it's just based on the style of the cough. So we do that like audio analytics as well. And we use obviously neural networks, a variation of neural networks for all of those problems. And yeah, don't get me wrong, our team does it. I'm not involved in the project where we do audio analytics. There are experts who are in that, experts in that area, in audio analytics area. And then disadvantages of neural networks, it's very slow to train because it takes a lot of iterations, a lot of calculations of, because each of the neurons will have to be like calculated for their weights and bias of each layer. And then because it is, the architecture becomes very, very complex, or like multiplies with each of the hidden layers we add. So it takes as much time to train it as well. And then it's almost impossible to understand the predictions. Again, it's very hard to explain why a particular output came out, but you can always use the results because it's one of the best performing techniques. You always use it when the explanation is not needed. And in the recent times in the industry, a lot of companies started doing explainable AI, explainable artificial intelligence. The goal of those initiatives is to create these artificial intelligence neural networks so that someone can explain it to a business user or to regulatory authorities, whoever is like, whoever they have to answer, basically. So there is this concept of explainable AI that is becoming a hot topic among the companies, among the tech companies these days. Any questions on it?
Yes, explainable AI is like the results can be correlated with a theory or give a reason for the result. Is it right? Yes.
Give a reason for the result. That's exactly what explainable AI is. So let's say in the US, right? Let's say if someone is applying for a credit card and the bank rejects their credit card application based on their model. They use some machine learning algorithm in-house, and they say the model says, reject this application, right? But the bank should be able to explain their model to a regulatory authority if that person, decides to say, hey, this bank is being, let's say, partial to one kind of people and partial to, is rejecting all the applications from a set of people. The bank should be in a position to explain why the model performed that way without using the data that might actually discriminate people. I hope I answered your question.
Thank you very much.
Sir, one more question.
Sure, ma'am.
Sir, actually, we have trained a particular model on a set of patients' data set, let us consider, like related to COVID. And now you can see that as the symptoms varies, some of the COVID patients are affected with black fungus or white fungus. So I have built a model. The model has been deployed, and this model is capable of predicting only the COVID symptoms.
Okay.
Now, the same model which has been deployed to that, can I add additional features so that whether this model can predict by taking into account those features also, is there a possibility for this person to develop a black fungus? Because some of the comorbidities, those are the factors. If I add, can that deployed model can take these additional features and provide the results, sir? Or I have to develop the model again and deploy it?
So I will take this answer in two different steps. One is that you could build a model which is a multi-class prediction, right? Multi-class prediction or multi-label prediction, I mean to say. So there are like some machine learning algorithms you could use to predict like two different features, right? One is whether the patient will get COVID or not. And the second target variable, like I mean to say there are more than one target variable in the machine learning algorithm. And the second target variable will become your, whether the patient will develop black fungus or not. But one caveat there is that whether you have labeled data for it already or not, right? Because for COVID, you might have, like if you already deployed the model, you might have used labeled data to train the model, right? When you develop the model. So the question becomes whether you have that training data available with black fungus as well or not. That's the first question. And you could, again, as I said, like you could modify the existing model to say, hey, I am adding another target variable, use the same data, but I'm adding a second target variable. It becomes a multi-target, prediction model, basically. In other terms, multi-label target variable. So you could deploy the same model with the same data, but you'll have to have the training data ready for it. If not, you could actually, again, I generally don't work with multi-label prediction models because of the kind of I don't know if it's data leakage, but I don't want my prediction for the first target variable to impact the second target variable. If I were you, I would actually pick a different model. It could be the same data. You don't have to repeat all of the steps, right? Because you already have the pre-processing, everything done. You just reuse that pipeline and only change the target variable to predict black fungus / white fungus, whatever you want to predict, instead of making it a multi-class prediction problem. If I were you, I would choose a different model, but just change the target variable as a separate, separate model.
Okay, sir. Thank you. Thank you, sir.
Oh, thank you. It's a very interesting question, and I'm curious actually to see your model.
Yeah, I'm working on that model now, sir.
Oh, okay. It looks like you are in the healthcare domain. And I have a weakness for healthcare. Weakness as in I love healthcare analytics so much. Weakness as in, like, my heart melts when I hear healthcare analytics. That's an area where you can really create impact for human lives.
Yes, sir. Thank you, sir. Thank you for asking.
Any other questions, anybody? All right, let's move on to the hands-on. I am going to go to my Jupyter notebook. I'm going to actually give you like 5 minutes here so that you can download Anaconda distribution for Python, and we can get started using that. And can actually at least like 5 or 10 people respond to me if you have experience with Python or not. And if someone like does not have any experience with Python, please do speak up so that I know that you are very new to Python and I'll start from scratch.
Mr. Siddh, I'm new to Python and I would love to learn from the scratch.
Thank you for speaking up, sir. I didn't get your name but we'll do that. Felix. Hi, Felix.
Thank you. Could we get the data set or should we download it from Kaggle?
If you can download it from Kaggle, that's the best, I would say, because Kaggle actually requires you to create an account to download the data. So I would say get it from Kaggle using this link. But any one of you, if you cannot get it from Kaggle, here is the data set I posted that I downloaded from Kaggle. And in the chat, I actually posted a link to download Anaconda as well. All you have to do is just search, like go to Google and say, hey, download Anaconda Python. And the first link that comes up is the individual edition Anaconda. You go there, you download that thing, and it installs Anaconda distribution in your machine. And when you are installing it, if it asks to make it your default Python environment, please check that box and make it your default Python environment in the computer. Okay, in the interest of time, I am going to give you about 3 minutes to download this package and then install it. Probably 3 minutes is short. I'll give you 5 minutes. We can wait for 5 minutes. You can download this package and install it on your computer so that we can do it as we go in the presentation today. And if anyone has any questions or any issues downloading or installing it, please do speak up. Don't think it's the problem only for you. There might be like other people who are facing the same issues. And if you answer that, we might be answering someone else's questions as well.
Mr. Sid, could you tell us the author of the data set, because there are a lot of diabetic patient pre-admission data set in Kaggle.
I actually shared a link just now on the chat. If you follow that link, it should take you only to one data set.
Thank you. Thank you very much.
Sure. Okay, I don't know if Shai Joman is still on the meeting or not. Sorry, Shai Joman, I did not see your message at the right time, so I could not respond. Yes, the class will be at maximum up to 1:30 p.m. today. We might finish a little early, but based on the pace we are going, I think it will take up to 1 o'clock at least. But yeah, it will definitely be done by 1:30 for sure. All right, we'll wait for another minute or two before we get started. Anyone has any questions so far, or were you able to download? Well, in a session like this, I don't expect 100% of the people to be able to successfully download and install, but I hope at least 20% of you guys or 30% of you guys are able to download and start along with me today. All right, we'll wait for one last minute. Okay, I received a question that it is asking for a sign-in. I did not download this in the last 2 days or 3 days. And like I have downloaded Anaconda a while ago because I use it every day. I don't know if it's prompting for something, but generally this is a free edition. So if it's asking you to like sign in or something, you can create an account with your email ID and it should be free. All right, everyone, let's get started. I don't know how many of you were able to download it and install it. If you did install, all you have to do is open your command prompt on Windows machines or a terminal in a MacBook machine. And then if you have a default internet web browser in your machine, all you have to do is type Jupyter Notebook, and then it will open up a Jupyter Notebook in your web browser. If you have Anaconda Navigator installed, like when you install the software, if it installed Anaconda Navigator, the easiest way is to go into Anaconda Navigator or open Anaconda Navigator and click on Launch button, which is just below Jupyter. I don't know if I have I do have Anaconda Navigator, so let me open it up. Oh, wow. What a navigator error. Okay, my navigator is not working. I hope your navigator is. Mine is a very old installation of Anaconda, so it might be version changes. And as I said, if you have just installed and you don't have the navigator, all you have to do is for the typo, type Jupyter, Jupyter, Jupyter space notebook into a web browser, sorry, not web browser, into a command prompt or terminal, and then press enter. It should actually start a command prompt or a web page, which looks like this.
Is it necessary to have the CSV file in the same folder?
It is easy that way, so that basically what happens is when I create this Python program, right? If it is in the same folder, all I have to do is just provide the CSV file. If I don't have it in the same folder, I'll have to write the entire path, like let's say C users, and then whatever your username is, let's say something, and then provide the full file path if it's not in the same folder. If it's in the same folder, you can just give the file name and it identifies the file in the same folder. And again, where your terminal is, right? When you start this one, this folder's open wherever you started your terminal from. Like right now I had like CDA Puri, that's my username. That's where the Jupyter notebook would start. And I actually navigated from there. I went into like programming, and then for this folder, FDP. So you can navigate through the folders on Jupyter Notebook. That is the easiest way. And then wherever you want to create your problem, right, or to create your new program today, you can create a folder and then start saying like, hey, create a new folder here or new file here with whatever is the interpreter that is available for you. And you can also create like new files if you want to create new folders if you want to create folders, and then put your CSV file there by uploading here. Like for example, I'm going into machine learning. Here is the file. I already have it in this file, but let's say if I don't have the file in this folder, I can go there and whatever the file I want to find, I can just find it and then come back here. Okay, some image. I can upload that image here. All right, I think we had almost like 12 to 13 minutes to get started. I hope at least some of you were able to come to this step. And then all you have to do is start a new Python, whatever version that is available for you, start a new, and then click on this one. It will open up a new web page like this. You'll only have like one line here, and this one says untitled. You can rename the file to whatever you want, and you will end up with a prompt like, with a cell like this. Any questions so far coming to the Jupyter notebook? All right, I take it as no questions, but whoever is working with me on this, we can get started. Yes, Felix, I can share this code. This is my own, so I can share this one after the session. So the first thing to do in Python is to import the necessary packages for the program. And actually don't look at all of these and be confused like, hey, how can we download all of these, right? Let's start with whatever we need first, right? Let's import pandas as PD. and NumPy as NP. These two are the absolutely necessary packages to get started. So let's just do these two. Import pandas. Pandas is a package which will create data frames. Data frames are the digital structures which work like database tables, but in Python program. And a NumPy is numerical Python. It has all the mathematical equations, calculations that we need. So import pandas as PD, import NumPy as NP. These are the these are the only two lines that you need right away to get started. Moving on, what am I doing in this first step? So this one is a setup. You don't have to worry about it. It's just excludes or ignores some of the warnings that that are generated during the process. So don't worry about those warnings. If you see that warning, we can set this option. So the first step to do is to read the data into a pandas data frame. And because I have the file, the CSV file, in the same folder as my IPython notebook, all I have to do is pandas, like PD is the pandas. That's how I imported pandas as PD. So all I have to do is pandas.readCSV is a function. And then I do pd.readCSV and I provide the file name. And that data will be loaded into this variable called full data. That's the variable I'm calling it. You can call it anything. And at any point, if I'm going fast, please ask me to slow down. I don't mind slowing down for a bit, but I just don't want to be like holding up the presentation if if it's too slow. And then if you were able to actually read the data into a variable, okay, do anyone need more time to get to this step? If not, I'll move on. If yes, I'll give you a minute or two to come to this step. I can only wait for you if you speak up. So sorry to put pressure on you, but that's how I'll know that I'll have to wait for you.
Yeah, I could type the first two lines and the sky, that is the third line from, and importing the other packages. I did not type.
You don't have to. We'll actually come to that step by step.
Should I
All
type
you need is the
simultaneously, or shall we just observe and learn, and then once you share, shall we execute it?
Absolutely, that works too. I mean, whatever works for you. Well, I'm like, I know. I'm guessing it is Felix who's talking.
Yes, yes, please. Yes,
okay. Hello, sir. So yeah, I know that works for you. I just wanted to make sure that, like, we'll hear from a few other people, see like what is their preference if they wanted to execute it along with me when I'm here. Like, if, in case there are any errors, we can fix it together.
Yes.
Okay. I'm going to Okay, I received another confirmation that they want to like execute along with me. So let's wait for them to catch up, and I hope they're catching up. And if you are not catching up, please do let me know so that I know to wait.
Sir, I have installed the Anaconda.
Okay.
Now I have just opened the Jupyter notebook.
Okay.
Now, in my browser, I can see the Jupyter has been opened.
Okay. The first step you'll have to do is you will see one cell, right? You will have to type these first two lines. Import pandas as PD and the highlighted text in the shared screen. Import
Sir,
numpy as NP.
Sir, I'm getting three tabs actually: files, running, and clusters. Where I have to just open this new
Oh,
file,
okay.
sir?
So you are still in this one in this window. What
Yes,
you
sir.
have to do is click on this new here.
Okay.
New, I don't know if you can see my screen, new here. And then whatever the Python version that is available for you, click on one of those.
Okay, sir.
It should say notebook and click any version that is available for you.
Okay, sir.
And then it should open up a page like this. Well, it doesn't show all of this patient readmission
Sir, it's
prediction and
loading,
data
sir.
import.
It's loading, sir. Yes, sir, I got it.
Okay. All right. Yeah, you will see a cell like this, and you start typing import pandas as PD and import numpy as NP. For now,
Okay,
all you need is only these two rows.
Yes, sir. Thank you, sir. Thank you.
Yeah, sure. All right, once you have those two lines typed down, I don't know who I spoke to, but yeah, along with that person, if all of you are following, once you type down those two, oh, actually, one thing I forgot to mention is, right, you will have to press Shift Enter to execute that cell and create a new cell for you. Hold Shift and press Enter, or you could highlight that cell and click on this Run button here. The shortcut is Shift plus Enter. And then once you have executed that one, you will, there will be a new cell that comes up. And in the new cell, type down, whatever the variable you want to call it. I say full data equals to pd.read_CSV because we are reading a CSV file. There is a function in pandas to read a CSV file, which is read_CSV. And within the parenthesis, provide your file name. And when that executes, you press Shift Enter. When that executes, your data will be loaded into this variable full data. Don't worry about what have I done, like, examine this data and all of this. I made it for the presentation. I'll tell you what you need to write to execute the code. So once the data is loaded, type this full data, whatever the variable you used. If you follow it, like if you use the same variable, probably it's easy to follow my code. So if you better, I would recommend using the same variable name. And full data.shape will give you what is the number of rows in the data and what is the number of columns in the data. And if you use the same file, you should see the same numbers. You have to execute it. You have to press Shift Enter to see this. All right, make sure that you have the same data as I do because we are using the same data set. And to look at what are the columns in that data, like what are the variable names or what are the feature names, you type the variable name, the data variable name dot columns, and it will give you the list of all of the 50 columns that are available in the data. And when you are done with like looking at the column names, I am going to inspect the first 10 rows of this data to see like, how the data is looking inside it and what are the values in the first 10 rows. All you have to do is the variable name, the data variable name, full data dot head. Head is a command which will get the top whatever the number of rows you mentioned. So you say like full data dot head and give the number of rows that you want to see. And dot t will transpose the value. If I don't use dot t, it will be like how you see in database tables, right? All of these column names will be here and the rows will come here. I just transposed it so that I can see all the 50 columns scrolling down. And I want some participation here. So whoever is seeing this, or even if you're not executing it, I want you to tell me, what do you observe in this data when you look at this data?
Weight is not given, sir. Weight question mark is given, missing data.
Weight is missing data. Very good observation.
And then one more code, payer code. So many missing data is there.
In payer code as well. Good point again. Anyone else? I mean, you could say anything, right? I'm like, there are many things that are visible on this data. And someone actually pointed out one of the outstanding issues in the data. But anything you observe in the data first?
The data is of different types, like categorical as well as numerical.
Mm-hmm. That's absolutely right. And how about, because we're on the topic, what is the type of age column?
Age is discrete classes.
This in
Age is
range,
discrete classes.
range specification. Yeah. Age is
Right,
specific
absolutely.
range. Yeah.
Yes, it is right. It is discrete. And I mean, like, in terms of, because the data actually has the range, it becomes a string variable in Python. Though it is a range with numbers, but Python only identifies it as a string because it has special characters, the square bracket, the hyphen, and the closing parenthesis. So it becomes a string variable in Python. For a human to interpret, those are ranges. That's absolutely right. All right, very good observations. And I just actually listed down the same observations here. Look for null values or missing data. And is that missing data represented with a special character? And yes, that is written with a question mark in this data. In general, in Python program, if the value is missing, you will see NaN, like a null value representation as NaN as null in the data. But this one, in the input file, it is not null. It has a value of question mark, but that what it means is it is missing data in the input file. So what I've done in the next command is to understand the data, right? We'll have to see if there are any nulls in the data. So what we do is we take the variable name and we use a function called isNull. What it does is it returns true if the column is null, and it returns false if it is not null. And to count the number of observations, we use this sum function. Basically, what this returns is true and false, and the sum will count or add up all the truths in that particular column. So I did that for checking the number of null values in the data set. And as you can see, everything is 0 because there is no data missing in this data set. All the missing values are represented using a question mark, which is not a null in terms of programming languages. Any questions so far? All right, I take it as no questions. So because I know that all the null values are created or like represented using a question mark in this data, I have written a code snippet that will display how many number of question marks are there in each column. So I will explain the code here. If you can type when I'm explaining it, that's great. If you can't, it's okay. You don't have to see it in action like right away because this is not model building. It is just observing the data. So it doesn't change anything in our model building process. So what I have done is, right, I have taken this full data dot columns. If you remember, this is how we list the names of all the columns in the data frame. And I'm saying in a for loop, for each column in this list, check whether that each column data type dot d type will give the data type of that object, and the variable name, the pandas data frame variable name and square parentheses will give you each individual column to inspect. And then I'm checking for each individual column if the data type is object. Object is nothing but a string in Python. If it is object, it's a string variable, because everything should be string and everything will be string if it has question marks. If it's an object, I am checking, it's just a print statement which prints like each column is the column name, and then I'm printing a colon here, and then I am counting. I am taking the variable name, I am taking the column, each column. This is to identify each column. And then I am filtering the data with another square bracket where that full data each column value is equals to question mark. So basically what I'm trying to do here is that take each of the column and then check if that each column value is question mark in all of the rows, and check like how many are there, and I count them using this count function. So what it will do is it will print the number of question marks in each of the columns in the data. And as you can see, there are like race is 2273. There are like no question marks in most of these columns, except some of these columns, as someone already mentioned, weight has a lot of question marks. The entire data is 107,000, out of which 98,000 rows have question mark. Similarly, the pair code, 40,000 rows have question marks, and almost 50,000 in the medical specialty column. So I'm just observing right now what is the quality of the data. Like, are there any null values? Are there any missing data with a special character like this? So I'm just observing that thing right now. What the next decision is, what do we do with these columns with more missing values? Going further down, we'll see like what are we doing with it, but what do you think we should do with all of these null values in terms of machine learning? Participation, please. Any ideas? What can we do with these columns with missing values?
Sir, we can simply ignore it, sir.
We can simply ignore it. That's one of the options. That's right.
We can take the mean value and replace it, sir.
We can take the mean value if it's a numerical column,
Yeah.
like weight is a numerical column. Yes, we can take the mean value and replace all the missing values. But I mean, like, that is a right answer. I'm not questioning your answer, but I'm trying to think out loud, right? What happens if I am using the mean value for 95% of the data? Will that value make any sense, or will that value mean anything in the machine learning algorithm? Because can it distinguish between admissions and readmissions if all of the data has, let's say, same value? I'm just thinking out loud. So I'm just raising a question for myself and you as well.
Would you repeat the question?
So someone recommended that we could use mean to replace all the null values in the weight column, right? Because it's a numerical variable.
If 95% is not available, then we won't be accurate in finding the mean.
That's actually a very good point. We might not actually find the accurate value, but still we have 10, let's say, let's say even if we have 10 values, we can still calculate that mean. But as you said, it might not be meaningful to have the same value for the entire data, because the machine learning algorithm might not learn much from that feature, because we are saying like, all of these people have the same values for it. Very good answers. Thank you, guys. first thing, thank you for participation and thank you for giving the right answers as well. And I'm not saying like if you're giving wrong answers, you should not say. You can speak anything. I myself have given very wrong answers most of my life probably. So there is no right or wrong answer. It's something you don't know and you'll know it today. That's all. All right, with that missing values that we observed, I went on to identify or analyze numerical columns in the data, and there is a function called describe, which is on pandas. So I am doing my variable name, the data frame variable name dot describe, and I only want to analyze the numerical variables of it. So I'm saying include only number columns. And that's what it does. It includes only number columns to describe. And again, I'm using a transpose of it so that I can print it in more rows than columns. And what does this say as? First thing is the count. The count will print all the number of non-null values in each column. So all of these rows or all of these columns have no null values. And the count is exactly the same, which is equal to the size of the data. And it also gives mean, standard deviation, the minimum value in that particular column, and the 25th percentile, 50th percentile or median, and then 75th percentile and the maximum value in that column. Encounter ID, patient number, admission type ID, discharge disposition ID, admission source ID. As you can see, all of these columns are IDs. So the distribution of these values doesn't mean anything. Well, statistically, you can calculate the mean source ID, mean admission source ID, but does it mean anything? It doesn't mean anything because these are the codes used by, let's say, a hospital to identify different types of admissions into the hospital. So it has no meaning unless we know what is the description of that code. But the rest of them, they actually mean something. We can see like how the data is distributed. The time in hospital is the number of days in the hospital. The minimum value is 1. The 25th percentile is 2. Median is 4. And the maximum values is 14 days. Like there is someone who spent about 14 days in the hospital, right? That's a interesting observation to make. And there are like number of lab procedures. There are like, there are like 1 procedure done, 16 procedures done, which is 25th percentile, median is 30. And then there is someone who had like 129 procedures done as well. So this is one way of looking at how the numerical columns are distributed in the data. And we could also do a box plot for the same thing. So I typed down all the numerical columns in the data. And then I don't know if someone is executing. If you're executing it, I am saying the variable name full data, and I use 2 square brackets. The first one to identify, I am writing the columns in a pandas data frame. And the second one is to identify, this is a list of columns. Lists in Python are identified using the square bracket. So you will have to use 2 square brackets and list down the column names that you want to execute. If someone is executing it, all of these column names are either here so that you can copy, or if you executed the columns command up above here, the full data.columns, you can copy it from here, starting number of lab procedures, no, time in hospital here, and the number of lab procedures until number of inpatient. All of these columns is what we are exploring here. So you create a box plot. Can someone talk about like why do we use box plots, and is there anything that you can observe or learn from box plots?
For outlier analysis, we use the box plots, sir.
Spot on. Very good answer. Yes, we use it to identify the outliers. For example, if we look at this one, the box plot actually is here, and a lot of this data is going until here, like the number of emergencies, like it is going up to here. And how do we deal with outliers is one of the pre-processing steps in data. You can choose to let them be, or you can actually scale them or standardize them. So in our process today, I'm going to scale all of these or normalize all of these so that the variation, the outliers are not as far from the data as they are with the absolute values.
Sir, I am unable to execute this. I think I have to do the library import of matplotlib. I think.
Oh, if that is what it says, we came to the right spot. Okay, now if you need this matplotlib, what you need to do is write this line in the command, like in the package imports, import matplotlib dot pyplot. The name is mat, matplotlib, matplotlib dot pyplot, plot as plt. So you write this command in the first row, just below like import pandas and import numpy, type this one down. And then actually, because we are here, why don't you type down the import cbon as SNS as well? So matplotlib and cbon are two packages in Python, which are used for visualizations. We create all of our visualizations using these two packages. And when you type this one down, don't forget to press Shift Enter. We'll have to execute this. When we write it down, we see it, but it is not executed. The compiler still doesn't know that we imported this package. So we'll have to press Shift Enter again to execute it. Actually, I just realized I could do this if anyone is following. In the chat, I'll send it to everyone. These are the two lines you will have to type down and press Shift Enter.
Thank you, sir. Able to execute.
All right. I go further down again. Yes, you will be able to execute this command now. If you say plot and then kind is equals to box. So kind is the type of graph that I'm trying to plot. So I'm trying to make a box plot. So I say in the plot, I say kind equals to box and vertical equals to false. If I don't do this, you will still see the box plots, but you will see the box plots in this direction. It will go up instead of going horizontal, it will go vertical. Again, this is not absolutely mandatory to execute the machine learning algorithm. It is just to observe the data. So it's okay if you can't follow, you can just see it here. And then we had the discussion about like the outliers there. And similar to the numerical variables, we also have another describe function, which will create some summary statistics about the string variables in the data. And these are all string variables in the data. And we see the count as, because the count is always like, because we don't have any nulls in the data, the count is always 101766. But what it will also give us is how many number of unique values are there in this data. So there are like 5 unique values for race. There are like 3 unique values for gender, like, you know, most of them are female with 54,000 rows, and rest of them are male. And there are only 3 rows I've seen in the data, which has like unknown category, but it doesn't matter. Like it's only 3 rows. So we do have like 3 different unique values in the data. And in the age, there are like 10 different categories. One is like, you know, 0 to 10, 10 to 20. We have seen all of those ranges already. And the most popular range is 70 to 80 age group. And we have about 26,000 rows in that group. So just like that, you can see, or you can observe all of these string columns and their unique values in that list. And one thing I pay attention to is, can you make note of these 2 examide and cytoglypton? This one has only 1 value in the column. The number of unique values is only 1. So all the rows in the database has the same value.
Sir, I have certain columns as question mark, but in your display it is MC or maybe the top. Yeah. When it comes to weight, it is 7,500. But for me, it shows question mark. but I get the frequency right.
Okay. Then I probably might have processed something. Let me execute it again.
The frequency is lesser, sir. It's 50% only. You have lesser one and
no,
yeah.
this is right. I actually did some post processing on the data, like when I was doing the experimentations. You are right. It should be question mark with 98,000 rows.
Very exact.
Thank you for saying that. I actually did not execute this code after I modified the data for some of the experiments I was doing, like replacing the values and stuff. So I executed this code again now. So that is exact counts. And then I'm going to just see how is the target variable, right? For any problem, we'll have to first identify like, hey, what is the target variable looking like? And what you can do is your variable name, instead of square brackets and readmitted, you could also use dot notation, just like in Java programs, you could use dot and readmitted. And then I'm doing a value counts. What it does is it gives you, it's like in SQL, it's a group by statement that gives you group by value and the count values as well. So the value counts is what it does is it takes a group by and then gives you the count. So in the readmitted column, we have three values. One is no, one is greater than 30, one is less than 30. What it means is a patient was admitted after 30 days of the initial discharge, and the patient is readmitted under 30 days after initial discharge. So both of these are readmitted, but some after 30 days and some before 30 days. That's how the value counts are. Anyone wants me to slow down, or are we going at good pace? Can I keep going?
Till here, we are able to execute, sir.
All right, thank you for confirming. Anyone else have any questions or anything that you are facing trouble with?
Sir?
Hello?
Hello?
Yeah, someone's
sir,
talking.
If you, yes, sir.
Yes,
it's me,
go
Sir
ahead.
Srijivi. Sir, can you just copy and paste the coding, sir? Some of the coding.
Sure. I think until here it has all been exploratory data, like just observing the data. So I did not do it because it's not mandatory. But going forward, I'll make a note of it. I'll send it to everyone.
Okay, thank you, sir.
Yeah, especially when I have longer code like this, where you'll have to write down all the columns. Okay, I'm going into the next step, which is data preprocessing for EDA. EDA stands for exploratory data analysis. This is where we do all kinds of charts, bar charts, histograms to see how the data is with by categories basically. But before I do any exploratory data analysis, I'm going to drop off some of the columns. And here is the list of columns. You can see it on my screen, and I'm also sending it to you in the code, sorry, in the chat. And can someone reason out why have we dropped the columns listed above?
It has a very high missing value, sir. More than 30% of missing values are present.
That is right, madam. That is for the first three columns. Weight, payer code, and medical specialty have more than, I think, almost 50% missing values. So I decided to drop those columns instead of replacing them with a value, and that will create a bias because I'm using that variable which is imputed. So I don't want to create bias using an imputed value. I'm dropping these columns. How about diagnosis 1, diagnosis 2, and diagnosis 3? Anyone else?
Maybe they are irrelevant, doesn't contribute much for the classification.
That is exactly the right answer. I don't know if anyone of you have noted this point before. The diag 1, diag 2, diag 3.
Unique values are very high.
Exactly. They have very high unique values. Generally, when we are using categorical variables, we don't want to use more than, let's say, 10 variables. Like the column should have only up to like 10 values. If it's more than that, the contribution of each of the values will be very, very insignificant for the classification problem. So I'm going to drop these three. There is another ways of using this information, right? I'm like, these are not null, these are populated. You could use use these columns and, put like, if the DAG1 is greater than 100 and less than 500, you can create a category for it. So you could discretize the data and then create less number of categories instead of like 700 categories. You could use it that way, but I didn't have enough time, one reason, and the medical codes, right? I mean, like, if I don't classify them in a significant manner, it doesn't help in the prediction at all. So these are all medical codes. So I decided to ignore them for the process. And can someone talk about hexamide and cytoglypton?
It has only one level, sir, and there are no missing values. So single level doesn't contribute anything.
That is absolutely right, madam. It only has one value. So in a classification problem, if the entire data is one value, it's not going to contribute much to the classification problem. So it's not going to define which one is going into true or which one is going into false. So I decided to drop these two columns as well. I have pasted that code in the chat. If you want to execute it, you could execute it. The reason I'm saying you could execute it is that starting from here, the data will be modified. Until now, we didn't modify any data. So it doesn't matter whether you execute it or not. But if you want to follow along from this point, you will have to execute it because to see the same results, basically. So I am calling it columns to be dropped, and I listed down all the columns that I don't want. And then I am creating a copy of the data saying selected data and dropping all the columns that I don't want. Access equals to 1. We'll say, hey, we are dropping columns instead of rows. If it is access equals to 0, it will drop rows. Because it's columns, we are saying access equals to 1. And again, I am going to paste this code into the chat.
So I want to clarify. Initially, we had the three variables having huge data set, missing
Right.
data. That is
Right.
weight and payer code and medical specialty, and it
specialty.
Had, yeah. But how you specifically said that 50% are missing? Is there? It is missing because question mark is there, which says
right. Yeah, question mark is a representation of null values. So the number of question marks in each of these columns, right? For weight, it's 98,000 rows out of 101,000 rows, which is about 97%, right? So 97% of this column was question marks. And this one was 40,900 rows out of 101,000, which is again about 40%. And this one is 49,949, which is close to 50,000 out of 101,000. So close to 50% or 49%.
Okay, from the
calculations. Well, you could do that calculation outside or even here. I just did it outside the code.
Right. From the count and the frequency, you are calculating the missing values.
From the count and the number of samples we have. The total number of samples we have is 100, like 101,766. This is the number of rows in the data set. If you go all the way up to the shape, what we executed in the beginning, that will give you the number of rows and number of columns. And the number of rows is 101,766.
Yes.
Yeah, I just calculated percentage on top of it. All right, we executed this one. In case you want to see like what is the shape of the data after dropping, we dropped 8 columns. So now the selected data has the same number of rows, but less columns. Previously we had 50 columns, now we have only 42 columns. And then there is, I wanted to like investigate how many number of question marks are there in the new data set now after I dropped the top 3 with question mark, right? And I have this code if anyone is interested. Again, this one does not change the data, but if you want to execute it, here is the code. And the one thing with Python you have to remember is that it is indent dependent. Like you'll have to indent up to 4 lines after the for loop or after the if loop, otherwise it doesn't execute.
So the copying did not happen. Only the previous command got copied. The for loop.
Okay. Oh, okay. Thank you. is copy. So here you can execute it. I'll move on in the interest of time. So we see here the race is the only column which has 2,200 question mark values out of 101,000. So it's about 2% of the entire data. So we could use this one, we could use this column and replace the question mark with something else. And we'll define what do we do with it in the next step, basically. So if I go into the race and I do the value counts, again, this is a group by statement, and it tells me like, for each group, how many rows are there. And if you see like there are question marks, which are 2,273, and we see all the other values as well. So what are we going to do now is that we have this question mark, we want to replace it with some other thing. One approach is, as I said, you could use the most frequent value and then add this 2,273 to this most popular class. But for this particular purpose, I wanted to treat them as unknown arrays for now, because I don't want to create more samples of the Caucasian, but I want to see how these unknown people, people's readmission rate, keeping them separate. So what I have done is, okay, if anyone is doing the code, I need to import something. And that one is here, this line. So you'll have to write this code in the first row and then execute it as well. So what I'm trying to do here is I'm trying to do a simple imputer, which will use an imputation technique. Actually, I could have done this simply with a replace statement, replace all question marks with unknown. That's a simpler statement, but I wanted to introduce the imputers to you. So in the imputer, what happens is, it's not like a string replacement, but well, the effect is just like a string replacement. But what it does is, you for a numerical variable, if you want to do mean, you can do the same within the simple imputer. What you do is you define an imputer variable using the simple imputer. I'm saying the missing values are identified using a question mark. And I want to use the constant strategy, not mean, not median. I want to use a constant variable for it, and that fill value is unknown. So basically, I want to replace this question mark with a constant value unknown. This is defining an imputer object, and then I execute it on top of the data that we have right now, the selected data. In the race column, I say this is the imputer variable, and I fit transform. It is like a machine learning algorithm. It learns, it sees from the data, and then I'm using a reshape, which, well, you don't have to worry, but I am writing it so that I'm not doing this imputation on the entire pandas data frame, but only on one column, which is race. That is all this one is doing. So I'm going to share this information, share this code with you so that you can execute it. But before you do this, please do run that from sklearn.import simple imputer. And Python is case sensitive. So if it's a capital in the chat, you have to make it a capital in the execution.
So what is that values range from -1 to 1?
Sure. So this is a piece of code. As I said, like probably you don't have to worry too much about it, but I'll tell you what it is, right? The selected data of race, right? You might have seen this already, right? I mean, this is how we refer to a particular column in the data frame selected data. And the dot values gets only the values instead of getting a, generally whenever you do this, you select a particular column in the data frame, the result is also a data frame with one column only. When I say dot values, it will become an array. It will become a NumPy array instead of a pandas data frame with one row or one column, right? So it will become a NumPy array. So I am using this information in the NumPy.reshape. I am trying to do the reshape of this data into basically a single row / column. I think it's a single row. This -1 or 1 defines the positions, like how am I reshaping it? Basically, I am taking one row out, I am taking one column in, I'm putting one column in. That's what the -1 does. It basically transforms a row into a column. All right. After this is executed, I'm going to check my race values again. Now I see I execute the value counts. I don't see question mark anymore, but I see unknown because I changed the question mark into unknown category. So now this data cleaning is done. And then we move on to the output variable. We have the output variable, which is no less than 30 and greater than 30. But for the machine learning algorithm, I want to make it a yes, no problem or true, false problem. So I replaced all the no's into false and either less than 30 or greater than 30 into true, because both of them are readmissions. So I'm going to share this piece of code with you. You could execute this. This will transform the output variable from no minus 30, sorry, less than 30, greater than 30 into false and true. And when we are here, we are at the exploratory data analysis. So we pre-processed the data for EDA, the exploratory data analysis. And here is a little more interesting part rather than just the code. We can see some charts and graphs. I hope this part is interesting for whoever is not been executing so far. This might be of interest to create these graphs and stuff. So the first one is what I'm going to do is to see the distribution of the target variable or the output variable. I want to see how many falses are there in the database and how many trues are there in the database. And the Seaborn package has something called a count plot. So I just used that count plot and I said, hey, X is the readmitted variable in the data. So print that readmitted variable and count it and put it in a chat format. And then make the title of that variable. I mean, that is optional. I just put a name to the chat calling it distribution of the output variable. And the one above here, fig equals to plt.figure, fig size. This one is like a meta statement, which only creates what is the size of the data that we want to print. Or sorry, the size of the chat that we want to print. I made it a square plot with 6 by 6 size. This PLT is the matplotlib that we downloaded. And what we're doing here is that we are creating a figure using that PLT package matplotlib, and I'm creating that figure with a size 6 by 6. So I'm going to share this code with you so that you can execute and create the chat. I'm going to give you a couple of minutes to execute this statement so that you can see a chart in the graph, in the Python notebook, and it's always interesting to see visualizations rather than just the code. So I want you to be able to execute, whoever is following along, I want you to be able to execute the statement so that we can see a visualization. Please feel free to raise a question if you have any questions. Thank you for the confirmation, Felix. Let's just give everyone else a minute if anyone's executing it. Thank you for the confirmation, Shivapriya. So the next plot,
sir,
I think it's a minute.
Error, sir. Plot, I do not get it.
Sure. What does the error say? I don't know who spoke.
Sir, Siranjeevi, sir. Siranjeevi.
Hello, sir.
Sir.
What is the error you see, sir?
Sir, it is telling tuple object is not callable.
Tuple object is not callable. So you have a parenthesis which is just trying to call a function. Did you copy the code from the chat?
Yes, sir.
Do you mind actually sending me the code in the chat? You can just send it to me. Well, I'm sharing my screen, everyone can see it, but can you just share it with me, please?
So I have to share the error, sir. Error?
No, just the code is good. Just share the code.
Sir, whatever the code you have sent, I have just copied it, sir.
Yeah, if you copied it, it should not actually give any error because
Okay, sir. No.
I executed it, and I know some people were able to execute it, and I'm sure you might actually are using an extra parenthesis or something like that. Otherwise, it should be like able to execute it without any
Okay,
errors.
sir. I'll check it, sir.
Yeah, and I executed it again now. I just executed it, and it executes fine. Anyone else having any issues generating the graph? And all of you, I feel more comfortable if you call me Sid instead of sir. That's more comfortable to me. Just replace the R with D, and you got my name. All right, I am moving on. Sorry, I'm thinking you said your name is Chiranjeevi. Sorry, I can't wait for you. I hope you get that plot. I mean, even if you don't get it, it's okay because this is just exploration. It doesn't change the data, so you will still be able to do the rest of the code with us. In the next one, I just wanted to see how is the readmission rate based on age. So like, how is the readmission within each age group? So I wanted to draw a plot to compare, hey, within each group, how many number of people were readmitted versus how many number of people were not readmitted. So the plot for it is this. I am going to share the code with everyone. Oh, wait, everyone in meeting. So the code, what I'm doing is, right, it is very similar to what we have done above, the readmitted, but instead of printing just the readmitted, what I'm doing is I am printing the age group on the x-axis, and I'm using the color, the hue is color, which is readmitted. So basically, I'm trying to print readmitted true in one color and true readmitted false in another color. So that's what this graph is about. And then again, title, you call it whatever you want to call it. And then we see this graph, and we see, if you notice this, right, most of the age groups, you see that, like, the readmitted false is a little more than readmitted true. But in terms of statistics, you don't have to be following along the code. But if you see this graph, can anyone tell me what could go wrong if we use this inference, this statistical inference, saying, hey, all of these age groups are, having this similar readmission rate to admission rate? Because, it's all like minute change or a little bit less in each of the groups. What could go wrong with exact values? All right, so what could go wrong with exact values is that, right, we cannot generally compare apples to apples or oranges to oranges directly using exact values. Because, for example, if I say, hey, this one, the 10 to 10, hey, it's just a little less, like, just like how the 20 to 30s or 30 to 40s. But we cannot say it is exactly the same unless we see the percentage of readmissions in each group are very similar. So what do we do next? We calculate the percentages in each age group and say, hey, and now I can see in the 0 to 10 age group, more than 80% are not readmitted. There is only less than 20%, or let's say about 16, 17% gets readmitted, whereas anything above 10, almost until 80 to 90, or including 90, 100 as well, most of them are between 50 and 60%, or 50 and 60 2%. So all of these are comparable, but 0 to 10 is, it's not as bad compared to the other age groups. That's when we can say it using the percentages. And the percentage calculation is a little tricky one. I actually reused one of the codes I used previously. So I'm going to share that code with you. You can execute the code. But if you want to go, or someone is interested in going by what did we do here, I am going to create, or I am creating age groups, grouping by age and readmission. Basically, it's like SQL statement. I'm trying to get the counts by grouping into age and readmitted combinations. And within that groups, I am going to do another group by to create calculations of it, saying, hey, within those counts, within, let's say 0 to 10 age group, I got one group which is readmitted and one group which is not readmitted. I have the numbers. How do I calculate percentages? Is applying a function, and I don't want to dig deep into these function calls here because it will take forever. The lambda function is a function which is a single line function or a nameless function in Python, so that you don't have to define the function but write it in a single line basically. And apply is a thing which is used to apply a particular function on each row of a pandas data frame. And that's how I calculate percentages here. And then I unstack those percentages in the next one just to plot. So the last line is just to plot. The first line is to create a group by n counts. And the second line is to create, from those groups, I calculate percentages. And the third line is to plot those percentages in the graph. Anyone questions or facing errors executing this one? Thanks for confirming, Felix. Cool. Thank you, Dr. Pichmani. And then we move on to the next visualization. So just like how we did for age, right? We could do something similar for race as well to see like, hey, how many people of each race got readmitted versus not readmitted. And then we do the same thing, just like the age. If anyone is interested, you could draw this figure. But yeah, I don't think we need to spend all the time here because it's very similar to that one. I just wanted to explore the data. I'm just seeing it here. And again, the same thing. The story is not clear when you see this person, like these plots. It's always the readmitted is a little higher than the admits. The readmissions, sorry, not non-readmits is always a little higher than the readmits. So it doesn't tell the full story. So I calculate percentages and I see percentages here. Well, in this case, actually, most of it is very similar. But there is like African-American who have like a little higher percentage of readmissions. And then Caucasians also have a little higher percentage of admissions compared to Asians, Hispanics, and the unknown category that we replaced question marks with. And again, if anyone is interested in plotting this, here is the code for it. And this one, I could do the same thing for the number of lab procedures as well, a numerical plot. But I just wanted to explore a different kind of plotting technique, which is called a KDE plot. This one is in SNS, which is Seaborn. So what I'm trying to do here is that I am trying to see or calculate the percentage of or the density of readmissions based on lab procedures. So we do like number of lab procedures, and one of these colors, I think the blue is the not readmitted because I see the readmitted is false here. So the blue is the not readmitted and the green is the readmitted patients. And this one calculates the density of readmissions based on the number of lab procedures done. Like, let's say if I take an example of 60, I know, hey, if someone had like 60 lab procedures, the density of readmissions is a little less than, or probably a little higher because the green is higher. A number of readmissions is higher than, or likelihood of readmission is higher than likelihood of no readmission. So one thing what we can see here is, right, as the number of lab procedures increase, we see that the green area is more popular or higher than the blue area, which means that as the number of lab procedures increase, these patients are like, at a high risk of getting readmitted more often than they don't get readmitted. And if there are like less number of lab procedures, they don't get as much readmitted. And I think it makes intuitive sense just to look at, right? If someone is getting done a lot of lab tests, it means that they might have like a severe condition and they might get readmitted, sometime in future. And anyone is interested in seeing this one, here is the code for it. Okay, am I going too fast, or am I giving you enough time to execute the code? Anyone has any questions so far?
Here, the graph is bimodal. If it is not normally distributed, it is having two peaks. Is there any explanation you have to give for the dip for bimodal distribution?
That's a very good question. I would not I would not say you have to give an explanation. It's more likely in this way, right? Like if I have to explain to someone, what I would say is that if there are like more number of lab procedures, let's say more than 40, they might actually end up having the same number of lab tests, right? And like they might actually, there is a standard set of number of lab tests that people will end up getting. So I would say 50 number of lab tests is probably more popular. Like I mean to say, there are more observations in the data with 50 lab tests compared to 40 lab tests. That's the only explanation we need to give.
Can we say people, maybe the threshold of 40, up to 40 lab procedures, we can expect lesser readmissions, but after 40, maybe exactly 38, after 38 threshold of number of lab procedures, the probability of readmission is higher.
Right. Yeah, I would agree with that statement. I think I would just say 30 instead of 38 because the crossing point is right here. So this one's almost like 30. It's in the middle of 20 and 40. So I would say the same explanation with just a small correction of saying 30 instead of 38.
Excellent.
That's a right interpretation.
Thank you, sir.
Yeah, thank you. Any other questions? All right, I take it as no more questions, and I did not plot it for every categorical variable. Like you will not have enough time to execute everything here. But what we can do is we can do similar plots for all categorical variables and numerical variables with discrete values, just like the number of lab procedures, right? We could do the same plots. All you have to do is replace the variable name or the column name here, wherever you use the column name, and you can create the same plots for all of the categorical variables and numerical variables with discrete values. So that's the exploratory data analysis. And as someone just mentioned, right, that's how we interpret these exploratory data analysis. We say, hey, we learned this thing from this, right? We can say, hey, if it's like African American or Caucasian is white American. So either it's African American or Caucasian, they have a more chance of getting readmitted compared to Asians, Hispanics, and other unknown races that we have here. And again, we can say something similar for the readmission rates by age group. We say, hey, if the patient's age is under 10, more than 80% chance that he will not be readmitted. But whereas with all the age groups above 10 until 100, you have, close to 50% or close to 40% for sure chance of readmission. So these are the kind of interpretations or inferences that we derive using the exploratory data analysis. And this is essential before you actually jump into machine learning algorithms, so that you know what variables have some impact on readmissions. And then I am going to do a little more data pre-processing and feature engineering for the machine learning algorithm. So this is one step before building the model itself. We'll have to do just a little more data pre-processing, and we can create more features. That is the feature engineering part. You could create more features if you think those are more useful, helpful in our case. And one thing I generally say, I actually say it in my team as well, and I actually say it with many people that I talk to. Feature engineering is an area where you will become a very good data scientist from a data scientist. Basically, you can be a data scientist, use the all the data features that are available in the data set, and build a machine learning algorithm, because it only takes like a few lines of code in Python. You can build the model, you can build a machine learning algorithm. But what makes you a very good data scientist compared to a data scientist is how can you leverage the existing features and create new features so that you glean more value out of the data that is available to you. So that's a point there. I'm just reading my messages before I move on. Gender-based comparison can also be made to find readmission rates. So that is absolutely right, Dr. Pichumani. I just didn't do it because it looks very similar to age groups, but only two groups, of course, in the gender. But absolutely, you can make it. All you have to do is replace that age variable with gender in the group. Sorry, in the code. All right, going into the data pre-processing for machine learning, we have one learning or one caveat in Python machine learning is this. All of the machine learning algorithms implemented in Python only work with numerical values. They don't work with categorical variables. Well, they work with categorical variables, but we convert them into a numerical variable by encoding them. And we'll see one encoding example here, but I just wanted to make sure that you know this, why we do this. So when it comes to age, like all the other encodings that we are looking at, right? All of those categorical variables can be encoded using one-hot encoder. I'll talk a little more about one-hot encoder when we come there. But the age is a special case here in the data set, right? Because the age has some ordinal value to it, right? 0 to 10 range is always less than 10 to 20 range, and 10 to 20 range is always less than 20 to 30 range. Though it's a string variable for Python programming purposes, we know it has some ordinal value to it. So what I'm trying to do here is, right, instead of doing it as one-hot encoding, I am trying to convert it as an ordinal value, which is a continuous variable with numerical values, because they have the ordinal relationship between them. So how am I doing it? I am using this code for I in a range of 0 to 10. 0 to 10 gives me 0 to 9 values. And what I am trying to do here is that this is a string replacement operation. I am replacing this selected data is the data that was selected previously. And what am I doing is I'm replacing so if you see like the data was like this, right? In the values, the data was like 0 to 10 with this. I heard a sound. I don't know if it's my earphones losing charging. Let me just check it. Okay, they are definitely very less. I might actually have to switch off my earphones for a bit. I hope the audio quality is maintained. Let me just charge my earphones. Am I audible?
Yes, sir. Yes, sir. You are audible.
Yeah, audible. Oh, okay. That's good. I'm using the laptop speaker, so just wanted to make sure that it is audible. So if we see the entire data, like age data is mentioned in this way, right? It is 0 to 10 as a range. So what I'm trying to do is I'm trying to build a string that goes from 0 to 10, 11 to 20, or 10 to 20, and 20 to 30, 30 to 40, all of that using a formula here. So what I'm trying to do is this parenthesis, like the square bracket is there in the data. So I'm using that as a string directly. I am concatenating it with 10 into I, which is 0,
I'll have to use a string function here because 10 into I is a mathematical expression, which is a numerical expression. We cannot concatenate a string variable to a numerical value. So I'll have to use a string conversion, and I convert that into string so that I can concatenate it with this. And there is a hyphen here. So I put the hyphen, and then I create the max range of the group, again with the same formula, but instead of I use I plus 1 here, so that it goes from like 0 to 10, 10 to 20 like that. And then I'm replacing it with I plus 1 value. So if it's 0, it becomes 1. If it's like 10 to 20, it becomes 2. If it's 20 to 30, it becomes 3, and so on. So I'm converting my age from ranges into ordinal numerical values. I'm going to share this code with you so that you can execute. Yeah, and this part, this data pre-processing and feature engineering part, is something that modifies the data. So you'll have to execute this before going into the next steps, if you're following along. And I'll wait for 1 or 2 people to confirm that you were able to execute the code without any errors before going on. Thank you, Dr. Gokila. Thank you, Felix. Thank you, Dr. Pichmani. Let's move on to the next step. So I'm doing a little bit of feature engineering here. So I'm trying to create a new feature, which is called total number of visits to the hospital, by combining or by summing up the total number of inpatient visits, total number of emergency visits, and total number of outpatient visits. I'm adding all of them and creating a new feature called total number of visits to the hospital. And if I explain the code, again, the dot apply will run the same code on each row of the pandas data frame. And within that row, what am I doing? I am sending an input X, and I'm reading the column X of number of inpatient and X of number of emergency plus X number of outpatient. Because these are all numerical values, I can directly add them. And then access 1 defines these are the columns basically. So these are the columns that you have to access is mentioned by access equals to 1, and the data dot apply will make sure that it is being executed on each of the rows in the pandas data frame. So we are going to create a new feature here, not just the one that came with the data set that we downloaded. All right, I assume you were able to execute this code. And then for the next step, what am I going to do is I'm going to create 4 new variables, which are called lab result no, lab result steady, lab result up, lab result down. The reason for these 4 new columns is that there are about 20 columns in our data set, which are lab tests. They actually test for, metformin, repaglinide, whatever it is, right? Like there are different types of drugs that they are searching for, and they do the lab test for it. And the results out of it is that either they did the lab test or not, which is identified by no in that column. And they did test for it, and the value is steady from the previous test. So they keep the value as steady. And then sometimes the value from the previous test, the current test, the value from previous test will go up. So they notify it with up value. And there are like some rows where the lab test result will go down, and they actually mark it as down. So there are these 4 types of values possible for all of these columns there. So what I'm trying to do here is, right, I'm trying to get that list of all the columns here. And what I'm doing here in this list is that I'm trying to create a count of how many number of lab tests were not done. It's a no. and how many lab tests were done, but the values maintained steady. That's another variable I'm creating. And I'm creating another variable which says how many number of lab tests the result went up. And similarly, how many results went down. So what I'm trying to do here is that I'm creating these 4 new numerical variables not instead of, along with all of these lab results, the categorical variables we already have. And this is how we do it. And I'm going to share this code with everyone. And we create 4 more variables. So far, we created 5 new variables for our machine learning algorithm, apart from what is already.
Sorry to interrupt. Could you, the 14th cell, could you copy? Because that was not pasted.
Oh, that's right. We need this one. Thank you. All right, you execute the second statement first, and then the first statement for summing. It has to be like how am I showing it on my screen. The column should be defined first, and then this count. All right, if you have done so far, let's move on to the next one. And I'm doing another data preprocessing step. And if you remember some of these, right, we already talked about these in the slides. One of those is like we replaced the missing values, the question marks already. And then we are creating new features, this is feature engineering. And then some of those columns will have to you'll have to convert them into categories columns. The reason for that is, as I was saying, the admission type ID is an ID that the hospital used to say like how did the person get admitted into the hospital. So it doesn't have any numerical meaning to it, right? Because the IDs could be 1, 2, 3, 4, 5, 6, but we can't use them as is. The reason for it is that if you use 1, 2, 3, 4, 5, 6 as is, the machine learning algorithm will think, hey, 2 is greater than 1 mathematically. So every time 2 has, there is a 2, it thinks it is greater than 1. And, it tries to use that information in an ordinal fashion, which is not right, right? It's just an ID. Any ID is different from the other IDs. So what do we do is, though the values are numerical, we convert them into categorical variables. And the simplest command for that is that you take any column in data, you say that column is equals to the same data with an as type function. As type will convert the data formats in Python. So you could make it as a string or category, or like if it's a number, you make it int, int. And if you want to convert some some number into a float number, you can say float. So that's how we change the type of the column in Pandas data frame. And we are converting these 3 columns here. And I am going to ask someone, or probably I can ask the question in next two steps. So here we are converting the ID columns into categorical variables with the statement. All right. I hope you were able to use or execute the code. All right, moving on to the next one. We are looking at the duplicate values, like if there are any duplicate values actually in the data, and there are. I know that because I looked at the data. So what we are going to do here is we are going to drop the duplicates, and there is a function in Python in pandas data frame, which is called drop duplicates, and you define what variable should we use to identify the duplicate rows. I am using the patient number here, which means that if there is a patient number that is present on 2 rows, they are duplicates basically. They are duplicates of each other rows. So I'm going to drop duplicates. And then what I'm going to do is I'm going to keep the first encounter of the data element. You could use first, you could use last, whatever you prefer. But I'm just going with first here. And then there is this special command called in place equals to true. So what does this one do is, right, when we are doing our drop duplicates, we are trying to change the pandas data frame itself. So when that happens, if you don't use this in place equals to true, it creates a copy of the data frame. And then you'll have to like read the result into a separate variable. Let's say selected data 2 equals to this one, and you can remove this in place equals to true. But going forward, you'll have to work with selected data 2. That's because you are capturing that dropped duplicate values. You're only keeping the unique values into this new data frame. I'm not doing that. I'm actually doing it in place for multiple reasons. One is to save memory. Like right now, we only have a few tens of thousands of rows, so it doesn't matter. But when we are working on 1 million rows, the data size matters, and we don't want to keep creating duplicate variables. So I am going to change it in place. And then here we are dropping duplicates. While you are executing this one, I'm going to just go to my presentation pretty quickly. And here. And I'm just going back to the presentation here just to see what kind of pre-processing steps have we done like in today's session, right? So we had missing data. We did something with it. We actually imputed with a constant value. We had duplicated data. We deduplicated the process. We have outliers, but I'm only doing the scaling of it instead of like dropping them. So I did not remove the data elements. I did not cap the data elements, but I'm going to scale them using feature transformations. And the sampling, we don't have to do any sampling today because the sample size itself is small enough. So we did not do any sampling. So we kind of like touched upon different data processing steps, for our process today. All right, any questions or comments so far? I think I didn't ask for questions.
How we did the data imputation, the first one?
So the data imputation, if you remember that we had the question mark, we replaced it with a constant unknown for the race variable.
Yes, I recall.
That is the only variable we are using in the modeling with a question mark, because the weight and the, what is the other one? The medical division or something like that. I forgot the name of the variable. We dropped them because they had like a lot more question marks, right? So there was only race which had a question mark, and we imputed with, if you remember, we used a simple imputer. We used it with a constant and we replaced it with unknown. All right, and further down here. All right, any other questions? I'm actually going to ask you guys a question soon enough. So if you have any questions for me, please shoot. All right, I take it as no questions. Either I'm doing a very good job of explaining things, or or you guys decided not to talk. One of those. So let's move on. The next one is that, I mean, this is just a sample command. If you are interested in seeing, like, what kind of data columns do we have in the data, you just execute, hey, what is the D types, like the data types of each of the column in the data frame. You say data frame name dot D types. It will give you what is the type of the variable in the data. And we created all these 5 int64 values by calculating something. These are the feature engineered values. And then we converted these 3 into categories. And the rest of them are like, how they were read from the input file, objects and integers. Object is a string variable. All right, and then I'm going to use another drop command. I'm going to drop 2 columns here, which are encounter ID and patient number. Can someone tell me why did I convert these admission type IDs, discharge disposition IDs into categorical variables and dropping the encounter ID and patient number?
Because they won't be useful for the model. But admission type and discharge, they will add up to the type of independent variables.
That's right answer. The only thing I would add is, right, in any data frame when we're building the model, the IDs are of no value, like patient number, student ID. When you're using a student prediction model, the IDs are of no value except to identify each row. That's all it needs to do, identify each row, that's all. And you don't need it to predict something. And if you use it, the machine learning algorithm knows nothing of it, but will still use it, right? Because I'm saying patient number is this, and the model will interpret it as a numerical variable, and it says, hey, if I'm doing a decision tree, if the patient number is greater than, let's say, 100,000, this patient is more readmitted, and if the patient number is less than 100,000, this patient is not readmitted much. So it will make rules based on the value you give and the output variable, the correlation with the output variable. So these are the variables which have a correlation but have no causation. It has no meaning to influence the target variable. So we should make sure that we drop any types of IDs when we are working on a machine learning problem. So I'm going to drop the encounter ID and the patient number from our database. So I'm going to drop, I'm going to do features to drop is these 2. And when the selected data, I'm just checking like how many number of columns do we have in the data set. Actually, you don't need this. I don't want to stop the flow. And what am I going to do is I'm going to create a data set variable called model data, which is the final data set that we are going to use for the modeling purpose. And what it does is from the selected data, it drops 2 more columns, which are encounter ID and patient number, and it creates model data only. And then the target variable for us is the readmitted column, which is also in the model data. So I'm assigning that model data readmitted column into a variable called target variable. And execute this one here.
All right, so far so good. I hope it is. Any questions before we move forward, or any comments? Do you need any more explanation of any of the things that we have looked at?
So we are dropping patient NBR, but still, why we did drop duplicates? Sorry if I have missed out. Why we do the drop duplicates and then drop the...
Right. So if I drop the patient number before the dropping duplicates, there is no way for me to identify the duplicate rows in the data. So I am using the patient number to identify the duplicates, because the duplicate rows are identified if the patient number is the same on a couple of rows, right? So I use that patient number information to drop the duplicates. But once I do that, the patient number has no meaning in modeling information, right? It has only meaning in the data pre-processing step to identify the duplicates. So I do that before I actually drop the patient number from the data set itself. Does that make sense?
Yes, sir. Sometimes the repetition may be due to they would have come for several visits. Maybe it's not so in this data.
Right. No, actually, you're right. Even in this data, they have come for multiple visits. If you want to do that, you could actually create a separate data set by aggregating all of these encounters into one row, like, one row for each patient. The encounter is nothing but each visit into the hospital, basically. So you could convert this problem into the same. You're absolutely right. But for the simplicity of the problem, we are just defining each row as patient number, like each row as a unique patient.
Thank you.
Yeah, but in real life, if we want to do the same thing, we'll have to do the group by of all of the other columns, right? Because we have about 47 columns, and you have to do a group by of the patient number and convert using some technique, like, what do we do with the lab results from 3 rows or 4 rows? If any of them becomes yes, you might want to keep it as yes. If any of them becomes steady, or what is the latest value, you might want to just keep the latest value, right? You could do that kind of aggregation and create the latest or keep the latest row only.
So I did not get the last part. Her question is, when we are dropping the duplicates in one column, and later going to drop the complete construct, she's asking why to do the drop duplication in a variable. Am I right?
No, I didn't ask that.
I hope I answered your question.
Yeah, yes.
Okay.
Sorry.
Yeah, I think Felix, the question was a little different. And I'm guessing she is working with hospital data or medical data, so she knows it.
Right.
All right, interesting points, guys. Thank you for mentioning it. Yeah, and if you're working, I don't know who spoke, the lady. If you're working on this data like later on, actually, you might want to consider what you just spoke. You might want to consider converting this data into like patient number level data by aggregating instead of dropping the duplicates, by aggregating. And you could count like number of encounters as well as one of the variables.
Yes, sir, you correctly answered.
Yeah, no, I'm just saying, like, in the future, if you want to do that, you could also explore that option when you're working on it. All right, any more questions? All right, I take it as no more questions. Let's move on to a smaller step in the process, is dividing the data into train test data. I know you might have heard it from all the sessions this week. So when we have a data set for machine learning purposes, we always split it into training data and testing data, so that we train the model and we make sure that it is performing with the same level of accuracy on the test data as well. So we split our data into train and test, and sometimes you actually use a validation data set, a third data set as well. So you train and validate first before touching the test data at all, and then you validate on the test data at the end of development process. Right now, during the development, we are using training data and testing data both just to measure the performance of it. But the same test data will be called validation data when we are using 3-split of the data. And you do the development, validating it, and make all the modifications that you want to make to the algorithm. And then you will keep a separate set of data, which is called test data. You will only touch it once your entire development process is done. Any questions or topics on it, like comments on it?
Sir, our target variable is readmitted column. And
Right.
the model data, don't we have to remove that, drop that particular column and then do this train and test split, sir?
You are absolutely right. But because I'm not using that variable yet in the model, I am dropping them separately from train data and test data here. I could have done it in single step, like you said. I could have dropped the model data, readmitted from the model data right here itself, and then do the splitting. I just, somehow when I was developing it, I just made sure that it is dropped before I use it for modeling.
Okay, sir.
You could do it either ways, but it is very proactive thinking. Thanks for bringing it up. But yes, I have done it before I used it for the model. So here, what I'm doing in this particular row of code is that I am creating train data, test data, train target, and test target by sending the model data and the target variable into a function called train test split. So this is a function which is in the scikit-learn package of Python, which is the package for all the machine learning in Python. And that is here in this particular row. I am going to send, actually, I'm going to send all of these scikit-learn features to you so that we are going to use, we know that we're going to use all of these. I wanted to introduce all of these packages like when the code comes to that line, but it doesn't hurt to do it now and explain it when we are using it. So I would request everyone to copy this line of code for importing all of these necessary functions. So one thing I would like to highlight is like pandas, in the pandas, I'm including importing the entire package, similarly NumPy. But for scikit-learn, what am I doing is I am importing only the specific functions that I would need. The reason for that is scikit-learn is a big enough package. So it will load into the interpreter, into the RAM of the computer, which will occupy some memory on the RAM. So to avoid it occupying the entire memory on the RAM, I'm only using the functions, I'm only importing the functions that are needed in the program. That's why you see the syntax a little different from the previous ones what we have. We use like from the package dot the subgroup or the sub package and then the function name here, so that it only imports the necessary functions for the program execution. And then once you put all of these import statements on the top, you don't have to actually go onto the top, by the way. You can create a new cell here, just execute this one, and then go into the next line and create and execute this code. So what it does is it takes the model data, it takes the target variable, and I'm splitting 25% of the data as test data. So I'm using 75% of the data for training. And because I'm giving the test variable, most of the time it takes the target variable into consideration and it does a stratified sampling, because I am saying strategy, the stratify variable is the target variable. So basically, in the whole of the data, if I have like 50% of trues and false of the target variable, my training data and testing data will have 50% of each, 50% of readmitted true, readmitted false, and 50% true and false in test data as well. But generally that's not the case. Right now we have, and we will see that going forward, we have a little bit of imbalance there, but it's not very imbalanced that we have to like create the class balance. So we are using stratification of the target variable here. So it does create in the same ratio as in the full data set. And then this random state equals to 0 is just a seed number. You can give any random number here. So the reason we use any number or any random state feature here is, right, this train test split shuffles the data and it creates a random shuffle and then splits the data into target and train and test. When we say random state equals to 0, the results can be reproduced. If we don't use a random state, what happens is the next time you execute the same code, you will not get the same sample, because the random state is not given. It again shuffles the entire data and it again splits the data randomly, and it might not be the same sample as you got the first time. So just to be able to reproduce the splits, we use a random state variable, and you can give any number. As long as you use the same number the next time you execute the code, you will end up with the same set of training sample and testing sample. Oh, I already pasted this code so you could execute it. And then I split the data into, as I said, like train data, test data, train target, and test target. I'm just seeing like how many number of rows are there in the train sample and test sample. There are about 53,000. If I actually did that, I actually did that. Yeah, there are about 53,000 rows in train data, and there are about 17,000 in test data. And then within that train data, I'm just seeing how many number of like true and false are there. And to the ma'am who asked me that question, like, why did I not delete that readmitted before sending it to train test split? I just wanted to make sure that the stratification is working as expected in the after the split. So yeah, if you want to do that, you could just see like what is the shape on the train data on your side, and you could do the same thing for test. I think you don't need that code. I'm going to give you this value counts, which is a group by statement to see like, how many number of false are there and how many number of trues are there for the readmitted column. And once you get that count, you make sure that the stratification is done as you want it to be on both the train and test. And if you calculate the percentage of true and false in the train data and the percentage of train and false in the, true and false in the test data, the percentages should be almost the same, if not exactly the same, based on the rounding errors, but it should be almost the same. And then once you have done that, you are ready to drop the readmitted column from the training data or testing data both, because you don't want to have the target variable in your model data. And what that does is that called information leakage. So if you actually give it in the model data, what happens is you'll get more than 90% accuracy. When you build a machine learning algorithm, you might actually get more than 95% accuracy. If in real life, right? I'm like, generally, if you get a model accuracy which is more than 90%, you should actually question your model and say, hey, am I doing something wrong? Because generally the model accuracy should not be more than 90%. Well, unless the data is very clean and it is very likely to get that accuracy, yes, it is possible. But yeah, but if it's not the case, you should first question if there is any information leakage coming from training data, testing data, going into the target variable.
So I just got a warning when I executed this drop.
The train data drop, right?
Yes.
Exactly. So the warning is something you don't have to worry. It's totally fine. That is called Pandas chain assignment. And if you remember, on the top of the code, I had this line, which is called chain assignment. So I am saying that option to none. So don't give me any warning if if there is any chain assignment. So I'm going to put it here. If anyone don't want to see that warning message there, please execute this command first, and then you can drop. Well, now you can't drop anymore because your column is already dropped. Yeah, but you haven't executed it. You could execute this line first, or in the future, if you want to use it, you can do that. You set that option to none, and then you execute that command. You won't get any errors or warnings. In fact, it's not an error, it's just a warning. Yeah, for those of you who have already executed, warning is nothing, you can just ignore it. Any questions so far? So far we have done a lot of steps. Like if I go to the steps we need, right? We understood the problem. We understood the business need. The business need is to predict whether a patient will be readmitted or not. And then we obtained the data set that is needed for analysis. We downloaded the data from Kaggle, of course. And whether there is any sampling needed or no sampling needed. No sampling needed for our use case because we have only so much number of rows. And then we explored, we cleaned the data, we processed the data. We actually did explore using those charts we built. We have replaced the missing values. We observed the outliers. We are going to do something with them. We did not do yet. There is a simple pipeline that we could use at the end of it when we are vectorizing the data. So I left it for the last, and there are some graphs that we created already. Reduce the data if needed. We actually reduce the data. There are some unnecessary variables that we dropped, like weight and some method, like I think the medical department or something. Those are some of the unnecessary variables. We dropped them. There is no dimensionality reduction needed for this problem because it's not like hundreds and hundreds of variables yet. So we didn't do anything in that area, but we added new variables. We did some feature engineering. We added more variables. So far we have reached this step. And determine the type of data mining task. I think we have done that already because it's a classification problem we are working on. It's a true false. And the next step is to choose what kind of data mining technique we want to use. And I actually used none of the ones listed here. I actually used the logistic regression model. I used a random, I used a random forest. We can look at the random forest. So that's the next step going into the modeling. But before we do that, right, anytime we have a data set, like an entire data set to look at, we want to make sure, or we want to check if there is any correlation between the variables that we are using for modeling. The reason for that is, right, if you remember the pros and cons of some of these algorithms for a logistic regression or for a linear regression problem, if it's a linear regression problem, the correlation actually has some impact. We want to make sure that none of the columns are correlated. So there is a correlation matrix that Pandas creates. So I actually created this one. The rest of the code here is just to show the plot. That's all it does. If you are interested in knowing it, what we do here is define a figure and an axis in it. And an axis, we are saying like, hey, this is a mat show because this is a matrix of correlation. We are going to show a matrix of the correlation values that is here. That's what we are doing here. And for the plt.xtix plt is the package we downloaded, matplotlib. So what we're doing is xtix and ytix are the column names. We are just making sure that we are doing the column names. And for the xtix, we are doing the rotation equals to 90 degrees so that the names are not printed horizontally, but they are printed vertically so that it is like, overlapping the column names with each other. We print them in a 90-degree rotation. And then the tight layout, it will actually print all of this together in a tight layout. That's all it does. And then PLT show is the command which says like all of this, right? What it does is it renders the visualization, and the PLT show will actually show you the visualization. And if you want to save this image as a PNG, you can say fig.savefig with a PNG name so that you can save this image outside the pandas or the Jupyter notebook. And the size, I'm just defining it as 12 because I'm going to use a figure size of 12 by 12. This matrix will be 12 by 12. And I'm going to give this code here. Okay, there is a form. Is it for me or for participants? I'm guessing it's for participants.
No, it's for participants only.
Okay. Hey, give all positive feedback, okay? No negative feedback from me. Just kidding. You you give the feedback whatever you think is good. All right. Can at least one or some of you who is executing the code along with me can see this correlation matrix? Thank you, Dr. Pitchmani, for confirming. Yeah, I generally like seeing this visualization here. This is so cool to look at. Well, this is so cool to look at, but how do we interpret this value is a question basically. So if you see the diagonal is all yellow, which means they are absolutely correlated with each other because it's the same variable. Age correlated with age, 100%. Time in hospital correlated with time in hospital, 100%, of course, right? So it goes from that into the darker or thicker values of green if it's positively correlated. And it goes into darker, thicker values of blue if it's negatively correlated. And for most of these variables, yeah, they are correlated, but they are not alarmingly correlated that you want to get rid of some of these variables. Except for the number of outpatient visits with the total visits, because we created the total visits by joining these three, the number of outpatient, number of emergency, and the number of inpatient. So it's kind of known that those will impact the total number of visits, and it's given, but it's not as low so that I'm letting it be there. If it's like completely low, that the number of outpatients is always the highest number of visits compared to emergency and inpatient, we might want to get rid of number of outpatients or outpatient visits or total visits that we created. We may have to drop one of those if they are like very yellow in color. And if you see this dark blue in color is the lab result study and lab result no. These two are very strongly negatively correlated, and it makes sense, right? We have so many variables for lab results, and each of those variables can have only one of these values. It can be either no, or it can be steady, or it can be up, or it can be down. It can only have one of these values. So these are kind of correlated. Yes, that is right. And whether to drop it or not, it's totally up to us. Right now, I did not drop it. But if you are using a logistic regression or a linear regression model, I recommend doing the drop of at least one of these two columns, the no and steady here, because they are very strongly correlated. Whereas compared to up and down, those are not like as strongly correlated as you can see here. So that's how we read a correlation matrix. And we do that for most of the machine learning algorithms we build. Well, if you are using a machine learning algorithm like random forest, you don't have to even worry about correlation between the variables because it is very robust. It takes care of correlation between the variables by itself. You don't have to worry about it.
Mr. Sid, can we say that lab result no and lab result study are good predictors?
So that's a good question. Right now, I can't say anything because this is just a correlation, right? I don't know the feature importance of these. I'll have to know the feature importance of these to say whether they are good predictors or not. That will come in the later steps. So the feature importance is right. We generally get it after we train the model. At least in Python packages, that's when we get it. So far, I can't say it yet.
Thank you.
Did I answer your question?
Yes, Sid. Thank you.
Okay, thank you. So that's the last step before we go into the actual model building. So when we go into the model building, there is one last step before we execute the model itself. That is converting the numeric features, right? The normalization I was talking about. We want to normalize these so that the outliers will not have as much effect. The outliers are not outliers anymore because we are scaling them using right now we are using a standard scaler. The standard scaler is nothing but a G transformation, like a Z normalization. So that's what it does. The actual value minus the mean divided by standard deviation. Am I saying it wrong? Is it actual value minus standard deviation divided by mean? One of those. You might actually know more statistics than I do. I come from the programming background of data science. There might be people in the audience who knows more statistics than I do. Yeah, but that is the Z transformation. You can simply, you can go into the scikit-learn documentation to see what it does, or you can go just Google like what is Z transformation. I'm sure it is most likely the exact value minus mean divided by standard deviation. That's how the Z transformation works. So what am I doing here is that I'm creating a pipeline so that what it does is I select all the numerical features in the model data, right now only in the train data, and all the numerical variables. I get the list of all those column names, and then I am using a transformer, which is the standard scaler, which is the Z transformation. And then for the categorical features, I'm going to select all the non-numerical characters or columns. As you can see, this is exclude, whereas numerical is include. So this one looks like number, but it is actually excluding all the numerical values. So it's all categorical or string variables in this list. And then what I'm going to do is I'm going to use a transformer, which is one-hot encoder. And can someone tell me what is a one-hot encoder?
It converts categorical columns to numeric values.
Numerical values, that is absolutely right answer. And how does it do it? I don't know if you would like to answer it, or if you want me to answer it. Anyone, if you feel comfortable, please feel free to answer. How does that convert? If I take gender as an example, or race as an example, right? The data right now is in this format. I have the gender column, and within that column, I have male, and then I have female in that column. So when the transformation, the one-hot encoder happens, right? What it does is it creates two new columns saying gender underscore male, gender underscore female. And for the first row, where the value is male, it puts a 1 in this column. Oops. And then it puts a 0 in this column because it's not female. Similarly, for the second row where it is female, it puts a 0 in this column, and then it puts a 1 in this column. So this is how the one-hot encoder works. Basically, any categorical variable, it creates multiple columns for it, with each of the values being a column, and it puts 1 if the value is that on that particular row, and if not, if it puts a 0. And where one of the reasons we actually don't use the diagnosis codes, as I was talking about, right? That one has about 700 unique values. And if we encode that one, we are going to get 700 features, out of which only one of the values is going to have 1, and everything else will become a 0. what it does, what it means is it becomes a sparse matrix of one value and 700 and some zero values. So the machine learning algorithm cannot learn a great deal out of it because it's very sparse. That's one of the reasons that any categorical variable we use will try to keep it under generally 6 or 7 values, but 10 is the max. We try to keep it under 10 values. So that's how the one-hot encoder works. So what we do is, for the numerical values, we use a standard scaler to do the Z transformation. For categorical variables, we do the one-hot encoding. One thing to remember here is that when we get the feature importance after the encoding, right? I'm like, because we have to do the encoding, the feature importance will come to you only at gender male and gender female level. You don't get the importance of gender itself. You only get the feature importance of gender male and gender female level. If there are 10 categories, you'll get the feature importance in 10 variables instead of one variable. That is something to remember, and it's something you cannot do anything about, especially in Python. If you are using R is equipped to deal with categorical variables directly. It doesn't need the confirmation or the conversion into numerical variables. So you might be able to actually interpret the feature importance way more easy in R compared to Python. And then what am I doing here is that I am creating a, not exactly a pipeline, but a column transformer function which will do these two transformers. For numerical, I'm saying this is a variable name, you can call it anything. I'm saying for the numerical variables, use numerical transformers on these list of features. That is what we have defined here. And you can call this variable anything you want. And I'm saying, hey, categorical transformer, here is the categorical transformer that you want to use, and that the transformer is a one-hot encoder, and use it on these categorical features. Here, I'm only defining these variables where the features are, like what are the features and what is the transformer. Here, I am saying, hey, these are the transformers that needs to be associated with this list of features and this list of features. That's what the preprocessor does. And here is the code to create this preprocessor instance, which will, when we execute it, which will execute in this order. And I'll give you just a few seconds to copy the code and execute this one before we go into the next step. All right, we move on to the next step. That is, we have defined these preprocessors, the column transformers, but we did not execute it yet. So what we do is we execute it on the trained data first using a fit transform function. So one thing worth learning at this juncture is that all of the machine learning packages and the converters and the preprocessors in scikit-learn, they have at least two functions most of the time. One is fit transform, or like either fit or transform separately. So what it does is, right, you are building a model or you're defining a model, but it has to be trained on training data set, right? So you will use the fit function or fit transform function so that it fits the data on this training data. And if you use fit transform, it transforms the data using the processor, whatever you have defined. And this fit transform or transform is the same function name for many functions in Python. In Python scikit-learn package. So what am I doing here is that I'm fitting a preprocessor model using the trained data. So what it does is, right, during this process, it learns what are the categorical variables for each of the categorical columns, and it creates a transformation model for that data, and it learns it so that you can apply that same model for any of the future data sets, like the test data, basically. So anytime you're doing this, you make sure that you're fitting only on the training data, and you apply the same transformation on test data, and you don't use the test data in fitting. The reason for that is, in future, right? You don't know what the test data is going to be. So you want to catch whatever is coming in the future right now itself. So you fit only using the trained data, and you try to transform using the test data, so that if there are any errors, if there are like any unknown values, you will know them right away. Right now, I have put a keyword here which says handle unknown equals to ignore. So if it's a unknown value, all of the columns in the test data, like for example, gender, I have only male and female in the training data, and I'll create the model will create gender male and gender female columns when it is fitting the data for training data. But in the test data, let's say there is an unknown value, right? The gender value is unknown in the test data. What does it do? Unless I say this handle unknown equals to ignore, it'll tell you right away saying, hey, there is a new value coming in the gender format, like in the gender column. Do you want to do anything with it? And it'll throw an error first. So it doesn't do the execution, it'll throw an error. And it's good to know that error right now before going into production, right? After you go into the production, you don't know what the production data is, right? If the production data has unknown values, you will have to handle it in the training itself. So either you do that, or you make this handle unknown as ignore. What it does is it creates the gender male and gender female columns, but none of those will have a one value when it encounters a new value in the gender column, like unknown. So both of those values will become 0. And then I am going to create a vector. I call it vector because we are going to vectorize the data using the scaler and the encoder. We create all numerical values. So I'm using fit transform on the training data. I use the same processor, and then I transform the test data into a vector as well. As I said, scikit-learn in Python only uses numerical variables for machine learning. So I am converting all the numerical values and categorical values into vector values of numerals or integers and float values. So that is what these two things do. And then I actually used a full vector which transforms the entire model data. And again, if you remember, model data had this readmitted column because I dropped it only after training data and testing data. I'm going to model this, transform this entire data using the same transformer. The reason for this is, we'll see it in the next few minutes, that I want to use cross-validation instead of splitting the data into training and testing by myself. I want to use a cross-validation technique, so that the model does the splitting on its own, and it does it in iterative fashion. It does like 10-fold cross validation or 5-fold cross validation based on the parameter we provide. So that is the reason we are using it here. So I'm going to share this code now, and then here it is. Did I send it to someone? Yes, I only sent it to someone. Let me send it to everyone. I hope you were able to execute this code. Any questions, comments? Any questions so far? What have you done?
Sid, you were saying 5-fold and 10-fold. Is it something
right?
Bootstrapping?
It is not bootstrapping. Bootstrapping is a technique where we actually repeat the samples, right? But the 5-fold and 10-fold is probably simpler version of bootstrapping, if I have to say it that way. But what it does is similar to bootstrapping. What it does is it splits the data into training and testing. The bootstrapping term actually came in when it is only used for training data only, right? You define like, which sets of training data you want to use to train the model. That's where the bootstrapping came into picture. But the k-fold validation, like either 5-fold or 10-fold validation, right? what it does is it takes the entire data set and it uses, again, just like bootstrapping, it uses some of those samples for training and some of those samples for testing as well. In case of bootstrapping, you have the defined target variable, but the samples are taken into account, like, some samples at a time, basically. Does that make any sense?
Yeah, thanks. Thank you.
Yeah, sure. All right, I'm hoping you were able to execute that line of code as well. And then here is a function. I don't know if you want to look at this entire function, but let me explain what this function is, right? I could create a 2-line code to do the prediction, and all it takes is this, right? Actually, let me do it very easily this way. I already have a code, so I don't have to do it here. I do this, and then this one. So I already came to the results, but let me show you this thing. So in Python using scikit-learn, all you need to do to build up machine learning algorithm is this. You define what kind of algorithm you would like to use. And I'm using this logistic regression model. And this one actually is a function that we imported from scikit-learn. So I'm calling it directly, and it has a parameter. I'm actually providing a solver called liblinear. The reason for that is it's good on the simple data sets, like smaller data sets. The solver is good that way. And the difference between a lot of these solvers is how they handle the errors, basically, in training data. So if any of you know normalization techniques, like normalization of errors, like the L1 level normalization and L2 level normalization, it is the different solvers use different methodologies for handling those errors, basically. I'm using this liblinear, and if anyone is very interested in learning, hey, what is the difference between this solver and the other solvers, you can go into this website, the scikit-learn, their own website, package website, and go into linear regression here, and then you go into their page, and then they actually show you. I'm looking for that. Where do they show it? Oh no, why am I looking at linear regression? It's logistic regression I need to look at. So yeah, so here is the logistic regression, and they show you, here are the valid values for solver, and they'll also recommend, like, what should you use for small data sets. As I said, like, I was using liblinear because it's a small data set, is a good choice, and you could use this as well to make it faster on larger data sets. Right now I'm using that one, but before going there, actually, let me take one step at a time. So all you have to do is you define a function. You could even delete this one, just say, hey, logistic regression, that's all. It builds a model still. And all you have to do is use that variable name and fit using the training vector and training target, and then predict using the test vector. You don't provide the test target because the test target is the thing that we are trying to predict. So you provide only the test vector, the data, to the predict function, and then it gives you the prediction. So that's all it takes. These 2 lines is all it takes in for building a model in Python. But what am I doing here is that I am creating a function. Let me actually keep this just in case I want to refer to it, right? So what I'm trying to do is, right, I'm
to interrupt. In the previous line, should we replace the CLF function into LR classifier, the trained model?
We definitely should, yes. If I used CLF, yeah. No, CLF is not defined, so it should be LR classifier. That's right. Thanks for noting it. Yeah, whatever is the variable that you are defining as a model here, that is the variable you should use to predict. So here, what am I doing is instead of writing just these 2 lines, I'm actually writing everything into a function. What am I doing here is that I print what is the name of the function that I'm passing as a parameter, of course. I print that, and then I'm also listing the categories of the train target in case you are interested in the categories to know. Right now, we only have true or false, right? It doesn't matter whether we list the categories or not. And then I'm just calculating or measuring time that it takes to train the model. I saved the start time here using the now function, and then I do another date time now when the training is done, when the fit is done. I use the current time and minus the start time so that I know how much time was taken for training the model. And again, I use another start time here to predict, and then how much time has it taken to predict here. And I am not sure if we downloaded this package. There is a date time that is a package. So if you did not download it yet, let's go download it. So yeah, this is the one I am using. So download this package as well. And you don't have to like go all the way on the top and execute this one. You could write it in one cell, just where we are right now, and then you can execute it. And then it gives us like how much time it took to predict here, as I said. And then I'm actually doing some metrics here. So I'm calculating the F1 score between the test target value and the prediction that we are getting from here. From the prediction, I provide those 2 values to calculate to this function, which calculates the F1 score, the overall F1 score of the model, and the overall accuracy score of the model. You provide the test target and the prediction values, and then you can also calculate the area under curve. The function name is called ROC AUC score. You provide the same 2 variables so that it can calculate it. And then there's something called a classification matrix, which is like a matrix, obviously true, false, like the original true, false on the rows, and then the predicted true, false are on the columns. And then you see like, what is the matrix, like how many true positives are there, how many false positives are there, how many true negatives are there, and how many false negatives are there. So that's what this classification report will print. And there is a confusion matrix, which actually prints the number of rows, the number of samples in all of those 4 quadrants, like the true positive, false positive, and true negative and false negative quadrants. It displays the number itself, whereas this one actually gives you the percentage. Actually, it's the percentage of like precision and recall, basically. Any questions on this code so far? I'm guessing no questions. I'm going to provide this function to you. You can execute it. Copy. Oh, probably the size of the function is too big. It doesn't paste here. All right, I can do that. So let me do this. I will copy till here. No, it doesn't work. How about this? I know I can definitely copy this and paste it here. Oh, okay, it's pasting till prediction time until here. So you could copy until this one. And then the next one I'm going to send, please make sure you indent this code at the same level as your previous print statements, because this print, when you copy paste it, it will go here to the first column value, move it 4 spaces. As you can see, all the other rows have 4 spaces, but this one, the first one, does not. So please use 4 spaces there. I'm assuming no questions, so I'm moving forward. Yeah, I've created another function, but we'll come there later. So once we define this function, all we have to do is that create whatever the model that you want to use by calling the function. And then I'm going to do this here. I'm going to use this solver, but copy this one back here. I'm going to use the liblinear solver with this logistic regression model. And then I'm creating a variable called LR classifier. And all I'm doing here is calling that function benchmark that we just defined with 2 variables, right? The first one is the classifier variable itself. And the second one is a name that you want to call it. I'm calling this logistic regression. And then all you need is call that function. You don't need this 2 here. I'm just keeping it at the end of the code if someone wants to just do it in 2 lines.
Sid, we need the accuracy part also. The previous function was half shared. Yeah.
I think I did send it in the second message.
Yeah,
you see this one, right?
Yeah, till confusion matrix we have got. That also accuracy also we got. But the cross-validation function, I think.
Yeah, the cross-validation prediction, I did not go in there. That's a function we don't need yet. We'll go there in a little bit of time. So that's a different function. That's not the same function as benchmark. It's a different function to use cross-validation, the 10-fold cross-validation I was talking about. It is a function to use the 10-fold cross-validation. Right now, what we are doing is that we are using the train and test split that we have divided the data into, and training on the train data and testing on the test data to measure the accuracy and stuff. So all you have to do is you take this code, and when you execute this one, you'll actually get this output. It might take a little bit, just a few seconds of time to come up with this answer, but it will come up eventually. You can see it. And what it prints is this, right? First, how long does it take to train the model? And it takes about 2.7 seconds on my machine. It might take faster or slower in some of your machines. And the prediction time is way faster because it doesn't have to learn anything from the data. All it has to do is just predict. It predicts way faster. And then also the prediction size is only 25%, whereas the training size is 75% of the whole data. And it takes only 7,537 microseconds to predict. And then the F1 score of the overall model is 0.48. The accuracy is 0.68, and the area under curve is 0.63. And the classification report is this one. This entire thing is called classification report. And what it does is it gives the precision and recall for each of the class that we are predicting. Right now, it's only a binary classification. So it gives you precision recall for each of these classes and the F1 score for each of them and how many number of samples are there in each class. And I am going to take someone's help. Can someone define precision recall F1 score for me?
Yes, the precision is true positive upon true positive plus false negative, or in the sense we can simplify precision as how many selected values are relevant. And the recall is sensitivity part, and or it can be called as a hit rate, or it can the formula is true positive upon true positive plus false negative. So it can be in words we can say as how many relevant items are selected. So initially for this how much of selected items are relevant, and in the recall we can define it as how much relevant items are selected. So the recall we can call it as a sensitivity part, and the precision recall can also be called as true positivity rate, true positive rate, and precision is precision is like true positive upon true positive plus false positive, and F4 is a mean harmonic mean of two times precision into recall upon precision plus recall. And the support, I don't know what support is.
I only asked for those three. Support is very simple. Support is the number of samples in each class, in the true class. So like when we divided the data into train and test, there are like some rows that went into test set, right? In the test set, there are 10,747 false samples, and there are 7,133 true samples. It's the number of samples. That's what the support is. And thank you for defining precision and recall and F1 score. Absolutely right.
May add accuracy. Accuracy is the first thing we used to see. The recall metric is also called as hit rate or true positive rate, or it can also be called as sensitivity. Another specificity is there where we check how much is correctly omitted. That is true negative upon true negative plus false positive. And the more important thing is accuracy. Accuracy is true positive plus true negative upon the complete true positive plus true false positive, true negative plus false negative. So that is the equation for accuracy. So 0.69 is 69% our model is predicting.
Right. Thank you so much. Is it Felix?
Thank you.
Yeah, thank you, Felix. I appreciate all the inputs. You also defined the terms that we are not going to use today, but actually, I think we might actually use, because area under curve is there. Any of you know area under curve?
May I add to area under curve?
Sure, why not?
Yeah, we have ROC, receiver operator characteristics, and the receiver operator characteristic is a metric to classify that is yes or no. Yes is readmitted and no is not readmitted. So we are going to classify the target variable using ROC, and that is a metric. And another thing is area under the curve is also a numeric score, which gives the maximum. We have the percentage of correctly classifier. So how our classifier is performing. It is a performance metric, that is area under the curve. Initially, they used it in World War II for predicting whether a bomber flight is a bomber or not. So that was used initially to use this ROC and the AUC. So when the curve is near to the left side, that is the top left corner, then we are having maximum prediction. So here the area under the curve is 0.604. That means that 60% we are our prediction is correct. Am I right?
Thank you, Felix. And I also want to thanks Dr. Pichumani. He gave the like the simplest definition possible. You gave the explanation for sure. He also provided some definition for area under curve or the ROC curve. It's the plot between PPR and FPR, or the sensitivity and specificity, as you were talking about. It's the plot between those two. And yeah, thank you for explanation, though not taking any credit from you, Felix.
Thank you, sir.
So, Yeah, so I think I don't have to define those because we have already people are defining those for us. And what metric do we use, right? I'm like, that is the thing that I would like to discuss, right? Many a times accuracy might be 90% or probably 100% as well, but would that define the whole picture? It won't generally, especially when there is a class imbalance problem. Like, let's say I am doing the same problem with 10% people readmitted and 90% people not readmitted. I could build a model, not even build a model. I could say vocally, hey, 100% of the people are not going to be readmitted. I am correct 90% of the time, because that's how the classes are divided. So when we look at the accuracy, the picture might not be 100% clear, or the picture might not be as good as we think it is based on just one number. So we make our decision based what metric to use, based on many a times based on the business problem itself. And then the second thing is what is the important thing in the business problem, right? Like, for example, in a problem of identifying whether a tumor in image analytics, like whether a tumor is cancer or not, the accuracy, because you in the sample you might actually have 90% which is not a cancer tumor, but 10% is cancer tumor, or probably 5% is cancer tumor. So in that case, the accuracy is not the best metric that you want to use, but the recall of the true class should be as good as it can be with the model that you are building, because the recall has more importance. It is okay if you are getting a few of the false positives, it's still fine. You're thinking it is a tumor, and then you're trying to treat it proactively, which is still not bad. But you want to have the recall of your true class to be as greater as it can be, so that you are not missing any of the actual cancer cases. So that's one example where you can we will use recall more than using accuracy. So that's one example. And though the 68% accuracy here is looking amazing, well, or not exactly amazing, but looking very good, in my mind, it's not actually very good, it's only good. The reason for that is our classes, the true and false classes in our data, are divided in 40-60 ratio. So 60% of the data is not readmitted, 40% of the data is readmitted. So if I go and say simply, hey, everyone will not get readmitted, my accuracy is still 60%. So the model is helping us only in identifying that extra 8% only. It's not compared to 50%, it's 68%. It's 60 compared to 60%, it's 68%. Because the gold standard in this problem is not 50% true false. It's 60% because the class distribution is in 40-60 ratio. Any questions? Am I making sense there?
So can I add to the explanation?
Sure, go ahead.
Like the confusion matrix on the screen, we can see 9,623. It stands for the true positive, that our model is correctly identifying people who are going to be readmitted, and the true negative is 2,626. That is the true negative. For false positive, or we can call it as type 1 error, is 4,507, and the false negative, which is very dangerous, that is type 2 error, is 1,124. So when we have accuracy means 9,000 plus 9,600 plus 2,600 upon the whole numeric. If we calculate, we will get the accuracy of 0.69. We can cross check also. And similarly for recall, if we can see, if we can add the true positive plus false, that is false negative, that is 1,120, that is 9,600 plus 1,100, then we will be getting the true positivity rate or recall or hit rate. That is the equation is 9,600 upon 9,000 plus 1,100. That is recall. The precision is the 9,600 upon 9,000 plus 4,500. That will give the precision. That is the vertical one. and the specificity for which if we can add these two, and if we can say 2600 upon 4500 plus 2600, that will give us the specificity. So on the top, the row wise, if we calculate, we get the true positivity rate, and below we have the true, that is a specificity, or we can call it as we can call it as a true negativity rate, so negative rate. So when we calculate the accuracy or F score, we can easily calculate with this and cross check this this decimals. Thank you for this opportunity.
Thank you, Felix. You kind of helped me. I don't have to explain that. All right. So the next step, right? I hope all of you were able to at least execute this one, the model, and get the results. Anyone tried to execute the code and got the results?
Yes, we are able to execute and got the result. Exactly.
Thank you. Anyone else trying? Oh, thank you, Shivpriya. I like seeing it. Yeah. I think it's a simple answer, but I'm just going to ask question. So can someone tell me why I am going to post a result in the chat. Oops, didn't work. And someone got this result. We have done everything the same. Can someone tell me why is that number looking different than the number I have? They have a better area under curve than I do. They actually have a better F1 score as well. Can someone tell me why is it happening? All right. Why is it happening is it depends on the sample, basically, because the train test split is not exactly the same in my machine, and it was Shivapriya's model, and she shared the results with us, and she had a different metric because the sample on her computer was different from the sample, or not the sample, the split was different on her computer compared to the split on my computer. So how do we actually make sure that the model is performing consistent when we build a model like this across any machine, or across in a different setup, like in production, or in a user testing environment? How do we make sure that the values stay almost the same, like if not exactly the same, at least almost the same? That's where the I don't know if someone was going to answer that one, if I'm stealing your opportunity, but I'm going to answer that, move on. So that's where we actually use the cross-validation, like tenfold cross-validation, because each one split that I made, right, as I said, the split I have might actually give me, like, let's say 80% accuracy, and the split someone has, let's say Felix or Dr. Pichamani or Shivapriya had, that split, that might actually give them a different result. That might not give them 80% result, or that might only give them 60% result, right? But it doesn't mean that they did not build a good model as I did. It's all depending on the sample of the data that I split into train and test, and they split into train and test. So to make sure that the train and test split has little impact on the model itself, what do? Is we do a tenfold cross-validation, so that we split the data 10 times into train and test with the same ratio, like let's say 25% or whatever, and then we run the model on that train and test split 10 times, and we take the average of all of those models to say, hey, this is the average accuracy of this model for this particular data set. That's the That's the cross-validate prediction I was looking at, or at least I scrolled over. What you do is you use a cross-val predict is another function, and you provide the classifier, whatever is the classifier you're using. But instead of providing only the train data, I provide the full vector here because I am not splitting the data. The cross-validation is splitting the data into train and test, and it is doing it so 10 times using the full vector and the target variable. And I'm just calculating the F1 score accuracy area under curve, the classification report and confusion matrix, just like how we did it in this function, like with one split and doing it. This is to make sure the model performs consistently irrespective of the split. And if anyone is interested, I'm going to put it in the chat to execute, and we execute it in a similar fashion. You call it, you do the same function here. So the first one defines the function and the second one executes the function. And I'm using that using logistic regression again, using this liblinear, and you see the cross-validation result. The accuracy came down a little bit, but I think I am happy with it. The reason for that is now I know for sure with any kinds of sampling, most of the time, or at least the average of my performance will be 65% compared to the random 60% of the random guess, basically. So that's the cross-validated part of it. Any questions or comments so far? Oh, are we at 1:30 already? Okay, I am going to wrap it up in a few minutes. I'm sorry if I run late by a few minutes, like probably 4 or 5 minutes. I'm assuming no questions so far. And then there is the importance. Someone was asking about, like, can we see how important each feature is? And yes, you can see it. But again, as I said, you don't see the name of the feature as is because those names are changed. Now, if it is all numerical, you will see all of them as the first probably, you know, there are 10 numerical values. The first 10 columns are numerical, but the rest of them are the categorical variables and the converted values of it. Like, you know, the first two values could be gender underscore male and gender underscore female. And it happens similarly for the rest of the categorical variables. And I know we had about 40 some variables when we started, but the coefficients you see in the logistic regression model are way more than 47. They are about 140 because I know it. I have seen it. So these importance correspond to, or these coefficients correspond to each of the converted columns using the one hot encoder and the numerical converter that we used. So how do we know the importance of it? If the coefficient is large enough, it is important. If the coefficient is something like this e power minus 0.4, which is like 0.000718, whatever, this is like very least significant feature. So you could ignore this feature if you want to reduce the number of features, or you can just keep it there. It doesn't hurt. At least at the moment, and I'll show you like why isn't it not hurting. And then I did something similar with the random forest classifier. All I have to do was like get the random forest classifier function, and we already imported that function. So you define, just like LR classifier, you define RF classifier, and you call that same function with the random forest classifier passed to it. And we get a similar report of the training time, testing time. And if someone is making a note of it, you see the random forest always takes more time than the logistic regression because it's not as simple as logistic regression. It is taking 14 seconds compared to 2 seconds that the logistic regression took. And the prediction also, it was like 7,000 milliseconds. Now this is 70,000 milliseconds. It's actually not 70,000, it's 700,000 milliseconds. And then again, they have an accuracy, area under curve, everything looks almost similar to logistic regression model, which means that this data set can be built or can be modeled using logistic regression itself. You don't have to spend more time training a random forest on this data set. Yeah, this one is, well, I'm like someone who knows this function name, they can always go in and execute it and see the results. So I'm not spending much time here, but I want to jump onto the next section where actually we'll see how many number of features will make sense to our model. And this is kind of a feature selection, but we are not doing feature selection on our own, but we are using a programmatic way of seeing how many number of features are making sense. And there is a function called RFECV in scikit-learn. And if someone who knows the machine learning, theoretically, this is the recursive feature elimination process, but it is also doing it with cross-validation. So what it does is it takes all of the features first, and it does cross-validation with 4 values and see what is the accuracy for it, for that model. And it removes one of the features, and it creates 4 more samples with cross-validation equals to 4. And then it removes 1 less feature and creates, like trains the model and calculates the average accuracy for it. And it does the same thing, that recursive feature elimination, until it reaches 1 feature. And it trains a model with just 1 feature and see how that model performs with a cross-validation of 4 sets. I'm going to share this code because this is a very interesting one to learn how many number of features actually make sense in a given machine learning algorithm. So for this one, if you see, starting from 1, right, the accuracy was somewhere around 615, 0.615 or 0.614 if you use just 1 feature. And then the accuracy increased as you use more features, at least until 80 or 100 features, the accuracy keeps going up at least a little bit. And then after the 100 features up to 140, it's still increasing, but it's minutely increasing, probably insignificant. So if you want to optimize your training time, and if you want to know like what is the best like way of like using the best number of features, you decide somewhere around 100 features as the best for you. And how do I decide what 40 features to get rid of, or how do I decide what 100 features to use? You use this feature importance here. This is according to the train vector that we created. So from the train vector, I only use I'll have to sort it by the importance of this one, and I only use the top 100 from the train vector instead of using the entire train vector. Is that making any sense, or is it not making any sense?
Yes, we have the creep plot somewhere in the eigenvector where the elbow is near to the ground level. We will cluster, and in clustering we use the creep plot. I think here also we can use the threshold.
Right. Yeah. I'm not 100% sure. Or probably, at least, I'm not sure of that word used, the creep plot. But it is. It sounds like a similar concept. That's right. Similarly, we can use this plot to define what is the optimum number of features to train a model, and we can do this on any machine learning algorithm we are using, and we decide, hey, how many number of features should we use after a given point of time, right? Like, let's say you have hundreds and hundreds of features. After a certain point of time, if you're not increasing the accuracy anymore, it doesn't matter to use all of the features. You can reduce the training time by reducing the number of features you're sending to the model. And this particular one, because it has to do this recursive feature elimination, and it has to, for each of the features, it has to do 4 cross-validation, it took a little more time than the rest of it. It took about 9 minutes and 7 seconds to train and predict, and then plot this one. Any more questions on this? I know I actually ran over like 4 minutes from the scheduled time. I'm going to apologize for those 4 minutes, but I'm going to share this code right here so that if you want to see the recursive feature elimination in action. I hope I explained the recursive feature elimination clear enough. so that you understand what it is. Well, it's only the first one that actually defines the recursive feature elimination, and the second one fits the training. Everything else, all of this is to just determine how to plot this graph. That's all. Any questions, comments, any final remarks? I think I'm done for the day, and I'm actually done for this program, at least for this year. Any questions, comments?
Very live presentation, Sid. We were able to execute along with you, and very engaging. And thanks for giving the space for interaction. Fantastic session and experience, learning experience. I think your time is right now 1 o'clock midnight.
It's 1 o'clock in the night. Yes, that's right.
So thanks for your commitment and dedication. Wonderful session we had. Thank you.
Thank you. Thank you, Felix. And thank you, Dr. Pichmani. Appreciate all the feedback. After yesterday's session, I received that I had to speak a little slow. That's why I was trying to speak a little slow today. But I hope, yeah, well, we were right on time, in fact. So I think it's all good.
Any more questions? No more questions.
Okay, I take it as no more questions, no more comments. Thank you, everyone. Thank you for this opportunity. Thank you, Srinivas. Thank you for having me here.
I know you are. I know how busy you are. Even though
Thank you, sir. Thank you very much.
Even though you are busy, you accept our request, and you have given a wonderful session. And it's a very, very interactive session. I hope all the participants are enjoyed a lot with this session. Thank you. Thank you very much.
Sure, it's my pleasure. It was a great interactive session. Thank you, everyone.
You know, it was too late to you. Even though it is late, you have taken and you have given a wonderful session. Thank you.
Sure, it's my pleasure. Thank you for the opportunity. Thank you, everyone. You have a good rest of the day. I'm going to sign off now.
Thank you for you will be associating with our 2-week FTP. I am very much thankful to you. Thank you, sir.
Sure, no problem.
Thank you to everyone. Now the session is about to close. Now can we